Ladies and gentlemen, good afternoon. This is Pina Salente speaking. I'm the secretary of the 19th International Workshop on Neutrino Telescopes. On behalf of the local organizing committee, I declare officially open the conference. I'm immediately turning you over to the chairperson of the conference, Dr. Mauro MEZZETTO from the National Institute for Nuclear Physics. Mauro, to you.
Good afternoon to everybody. I'm Mauro MEZZETTO, chairperson of this conference. Co-chair is Elisa Bernardini next to me. I'm here to say a few words about the workshop and his history and the characteristics. Now, the workshop had been initiated in 1988 by Professor Mila Baldocciolin. In her picture, the conference should had to address the two main features of neutrinos. Namely, they are a probe of fundamental laws of nature. So neutrinos are a very important role to understand the features of our laws of nature. And they are a messenger for astrophysical and cosmological processes. So the two aspects are really characteristic of neutrinos. The conference since the beginning tried to address these characteristics. So it began in 1998, and traditionally the venue of the workshop, the next slide, the venue of the workshop was, the workshop was hosted in Venice by a public institution of Regione Veneto. The public institution is Istituto Veneto di Scienze, Lettere d'Arte, giving us a wonderful location placed on Canal Grande in Venice, next to Ponte dell'Accademia, really in center of Venice. Now we are indeed sorry not to be able to host you in this place, but the virtual format demonstrated to have very peculiar and very interesting characteristics. First of all, we had 947 registration. This is roughly 7.5 times more than our average number of registration. That's really remarkable. We were not prepared for such a huge registration number. We rethought entirely the format of the conference because we were convinced that we had to give room to young physicists to present their works, since in this period workshops are not so frequent. So maybe young physicists need to find their place to present their works. So we decided to open to parallel sessions, and we received roughly 240 abstract submissions, and we had to apply tight rules to decide which were to be considered parallel talks of 15 minutes, which flash talk of 5 minutes, because we had to fit the timetable of the conference. We could not enlarge too much the time of the conference. So a virtual conference really breaks many barriers and allow people to participate without many problems. On the other hand, it has been an exceptional effort for the local organizing committee. So let me introduce the local organizing committee. You will meet the local organizing committee members because they will be the conveners of the next sessions. So in Padova, the neutrino and astrophysics community is quite variegated. Somebody say that we are hypertrophic, but the people here work in many experiments like T2K, Per K, Super K, Dune, Icarus, Magic, Ice Cube, Luna, Enubet, plus theorists. So we are a variegated community. All the people here work together in a very positive and enthusiastic way. And without the effort of these people, we would not be able to organize this conference in this format. So really, I have to thank the effort of the local organizing committee that met in a virtual way all this time, but we apparently managed to organize this conference. The other important committee is the International Advisory Committee. In particular, in this year that we had to rethink everything about the conference, the suggestion, discussion, criticism by the International Advisory Committee had been very important for us and helped us very much to understand how to organize this conference. The last slide is about the timetable. Let me to introduce a little bit the timetable. In the next days and then the following days, we will open the conference at 10 a.m. CET time with parallel sessions. So the first 80 minutes will be dedicated to parallel tools. They are organized in 11 different thematic sessions, and they will go in parallel in 3 sessions. And you will find the link to the right Zoom room in any of these sessions. They will be followed by an hour of flash talks. The flash talk will be 2 sequences of 4 talks of 5 minutes, followed by 10 minutes of discussion, then additional 4 talks and additional 10 minutes of discussions. And these are the morning sessions. The afternoon session will be devoted to plenary talks for 3 hours. And then we will have 1 hour of again, parallel talks in the evening, just to favor American speakers that can find more comfortable this time. We will open several Slack channels to follow the discussion. So you will find these Slack sessions. We encourage everybody to use this channel to have a discussion about the topics of this conference during the conference, offline, whatever. And we hope to offer an appropriate instrument for this kind of discussions that cannot be done lively during the conference. So I finish my presentation and I leave to the other speakers. I really wish to everybody a good conference. Thank you.
Thank you, Mauro. I would like to inform you that the conference has been organized under the patronage of the University of Padova, one of the oldest in the world, celebrating next year 800th anniversary from its foundation. I'm honored to introduce you to the rector of the University of Padua, Professor Rosario RIZZUTO.
Good afternoon, dear colleagues, dear virtual guests of our university. I thank Mauro MEZZETTO and Elisa Bernardini for the privilege to participate in the opening of this workshop. It would have always been a privilege to open an important scientific meeting. But let me tell you that in these days, it is a particular pleasure and privilege. A year ago, exactly in these days, few kilometers from here, the first European case of COVID-19 was identified, an old man who died a few days later. And we would not have imagined that this would have opened a period that dramatically reversed our lives, reversed our way of being a community and carrying out our common activity, science, in this particular case. And we are all looking back. Unfortunately, we're not only looking back, we're still living a dramatic period. And in this dramatic period, opening a scientific workshop, so doing our privileged activity, what we love and what we believe is important and is always important. And I think that even this pandemic taught to all of us the relevance of science in society. So in this particular moment, opening a scientific meeting, a high-profile scientific meeting, is also telling to ourselves that the most fundamental part of our lives, our activity, I'm a biomedical scientist, so I am not exactly in this field, but I feel like a member of the broad scientific community. So I am a member of your community as well. And I believe that the idea that in these days we are back in business, back doing our scientific meetings, is a very strong moment, a very strong point of reference that we're living. So I'm really particularly glad. Of course, I'm particularly glad because this is a great meeting, because this is a meeting that has been going on for more than 30 years. This is a 19th workshop on neutrino telescopes. And this again, I thank the organizers for reminding that science looks ahead, and science looks and is always eager to obtain something more, is eager to, but also science works on what has happened before, and we build gradually, and we are never satisfied of how fast we move on, because we want to be very fast, but we can be very fast when we build on a tradition. And of course, we are very proud of the tradition of being 800 years, of being the university in which Galileo declared that he spent the best 18 years of his life. But also the idea that this is a workshop that has been going on for 32 years and is at the 19th workshop happening, I think tells us not only of the relevance and the vitality of the scientific field, but also on this capacity to work together and to move on. And let me conclude that if we look back, it's not only 32 years, but it's also the workshop that was founded by Milabado Ceolin. And it's very nice for me to correlate that in just a few days ago, we signed the opening of the university nursery to allow young women in science to have full opportunity to be supported and assisted in the very early phases of their career, and to reach the opportunity to have exactly the same chances and obtain the same results as their colleagues who often do not have the necessity to also to have a family and to take care of children. And we dedicated this nursery to Milabado Ceolin because we believe that her example, the example of the first full professor in the University of Padova, not in physics, but in general, the first full professor of the University of Padova, was the person that mostly represents the capacity, the ambitions, and the potential of all our women colleagues who are in science and are in university. So thank you again for giving me this opportunity to bring you the salute of the entire university, and I wish you a very successful workshop.
Thank you, Rector. The next person to address his welcome to you is the president of the National Institute for Nuclear Physics, Professor Antonio Zoccoli.
Thank you very much. It is an honor to be here and to welcome you on this workshop on neutrino telescopes. I would like first to thank Mauro MEZZETTO and Elisa Bernardini having organized this meeting. It is a long-term tradition for Italy and for INFN, and I'm happy that this is happening now. As Professor RIZZUTO was recalling before, we are facing very difficult times, and it is important in these difficult times that we still are able to carry on our research activity. I think the research will play and has to play a major role in this crisis, and it is important that all the research activity are going on. So to have all of you in this meeting, even if it is still virtual, is really important. And it's important that the community is meeting and discussing the future, the present, and the future of this in this field. Neutrino, I've seen also that there are, as Mauro was mentioning before, there are more than 900 people registered in the meeting. It means that is a great success and great interest. And was also mentioned that is more than a factor of 7 bigger number with respect to the past. So I was asking if the Venice location we was chosen before was not appropriate, maybe is not enough attractive, and the current organization is better. I'm joking, of course, but I'm really puzzled by the fact that there are so many people registered and attending to this meeting. For the National Institute for Nuclear Physics, Neutrino is a long-term tradition. We are working on these magic particles since the beginning. And I have seen, looking at the conference program, that we have Nobel Prizes, which are making will make very interesting talks on the past, present, and future of neutrino science, on gravitational waves, but also on neutrino anomalies by our, let's say, some proud, Italian proud, our Nobel Prize, Carlo Rubbia. So I'm also would like to welcome them and to thank them to giving this contribution in this conference. I've seen also Nando Ferroni, my predecessor as INFN president, which will explain us the future of the double beta decay. So I think there's plenty of very interesting talks, both looking and studying the neutrino properties, the implication on the electroweak theory, and also looking at the universe. So by using the neutrino as a messenger from the universe to understand the properties. And in this particular time is even more important, this aspect, because we have a new player in the field, which is given by the gravitational waves, which is adding a new messenger from the universe. So I think it's a very interesting moment in science for this topic, and I hope that all of you, all of us, will enjoy this conference and will benefit from the discussion we will have in the next days. So thank you, everybody, and have a nice time together in science.
Thank you, President. The conference has been co-organized by the Padua unit of the National Institute for Nuclear Physics and by the Department of Physics and Astronomy of the University of Padua. So please let me introduce you the director of the Department of Physics and Astronomy of Padua, Professor Flavio SENO.
Good afternoon to everybody. I'm very honored to be here to welcome you on behalf of my department. I take advantage of a so wide auditorium to advertise a bit our department. And I will start from history. We could say that we stand on the shoulders of giants. I don't dare to go back to Galileo Galilei, that maybe is too much, but I would like to point your attention to Giovanni Poleni, that was the first professor of experimental philosophy. The chair of experimental philosophy was appointed by the Republic of Venice here in Padova in 1739. Giovanni Poleni was a great scientist. He had collaboration, he has interaction with all the major scientists of the period, such as Newton and Leibniz, Bernoulli and Euler. And at that time, and probably also now, a very good way to explain physics is to do demonstrations, is to make experiments. And so Polanyi started to collect from all over Europe instruments, also older instruments, so like this astrolabium that you can see in the middle of the slide. And starting from them, we are collecting these instruments that are now put in a museum, the Museum of History of Physics, that contain more than 1,000 instruments. I will be very happy in 2 years' time when you will be in presence for the next Neutrino Telescope conference to show you this exhibition. I would like also to mention another important person for our department, that is Bruno Rossi. Bruno Rossi was appointed professor of experimental physics in Padova in 1932, and he stayed until 1938, when he had to leave Italy for the Russian law. In that period, he gave an incredible boost to the research, especially on the cosmic ray, but also he built up the new building, the new department. You can see here a picture of the beginning of that work. And in this moment, we are still in the building that was thought by Bruno Rossi. Then I would like to mention other two persons that are very connected to this series of conferences. Of course, Milla Baldo Ceolin and Marcello Cresti. They had an important they gave an important contribution to the opening of what we call now multi-messenger astronomy. And they opened the way to for a group of new scientists to start this kind of research that now is so popular and so important. And now the department is, the actual department is the result of a fusion of the former Department of Physics and of the former Department of Astronomy. It is a quite huge department. We are 138 faculty members, 73 administrative and technical staff, more than 70 postdoc, and more than 100 PhD students. And moreover, we have a strong collaboration with INFN and with INAF, which is the Institute of Astrophysics, National Institute of Astrophysics. So I will not tell you if we are good or not, but I would just to show you some results about our students. We have 3 bachelor courses, Astronomy, Fisica, and Optics. And then we have 3 master courses that starting from 2017 are kept in English. And they are Astrophysics and Cosmology, Physics, and Physics of Data. And then we have 3 PhD courses. In the next slide, you can see the increment of the number of the students. So you see in yellow is the total number of the students that in 4 years passed from 100 to almost 250. So these courses are really very attractive, at least for in the Italian region, let's say. And even more important, if you look at the right bin, that is the number of the foreign students. So you can see that now almost more than 20% of our students are foreigners. And that is really very important because, as you know, many Italians go abroad. And so we need to keep an equilibrium here in order to keep high the level. And I think that one of the reasons why we have this ability to attract students is also the strength of the astrophysics, astroparticle groups of the department. I will conclude just mentioning 2 sentences by Milla that you can find in the proceeding of the conference. And in the first one, she was closing the meeting, hoping for a second edition in next November. okay, we are here 30 years after, and so we can say that that was really a good idea and that she was very too shy in making that prediction. And I would like also to point out the other sentence to show the attention that Milla had for the collaborators and also for the technician and for the secretaries. And in all these meetings, he was always thanking Leopolda, that probably most of you knew if you came to Venice. And she said that the role in making neutrino telescope successful cannot be overstated. I think that it's difficult to overstate the importance that Milla had for the growth of our department and for science in general. And I'm very proud that just a few days ago, as our rector said, our university opened an asilo nido, that is a kindergarten for the people working in the university. Okay, I wish you a very successful meeting.
Thank you, Director. And now, the last but not least welcome address to you will be given by the Director of the Padova unit of the National Institute for Nuclear Physics, Dr. Carlo BROGGINI.
Thank you. Dear colleagues, dear friends, it is really an honor and a pleasure for me to welcome you to this 19th edition of the International Workshop on Neutrino Telescopes. Well, first of all, let me thank Mauro MEZZETTO, and all his collaborators who really did an enormous amount of work in this not easy period. And I could see I'm sure it has been much more difficult to organize a conference like this, not in person, than in the past to have this conference in Venice. So really, I thank him and his collaborators a lot. Then, I mean, I remember, this is a kind of conference I like very much, since I remember it was at the second edition, I think, of this conference that I met for the first time Milla Baldo-Ceolin. At that time, I was a postdoc in Switzerland, and we were studying the possibility of having a neutrino telescope placed inside the lake. The first in the region around Neuchâtel, and then in the region around Gran Sasso. Roughly the dimension, I mean, the project was a cube with 30 meter side. And this, I mean, if you compare this dimension to the dimension of the detectors, which we are going to discuss at this workshop, you see how, in a certain sense, naive we were. In any case, how far we were from what is existing nowadays. But despite this, Milla was really almost prophetic in starting a conference like this at that time. I think it has been the first of this type in the world. I remember the sentence in Italian was un altro modo di guardare il cielo, which means another way to look at the sky by using not only photons, but by using also neutrinos. And also in the choice of the name, I think she was very careful, because, you know, telescope means to see far, and indeed Milla was able to see far. So at this point, I wish you a very interesting conference, rich of new results, but also and mainly rich of new ideas or new dreams, really in the spirit of Milla. Thank you.
Thank you, Director. And now I really thank all the people who have talked till now, and I'm turning you over the co-chairperson of this conference, Professor Elisa Bernardini from the University of Padua, who will be the convener of the next session. Elisa, to you.
Pina, thank you very much. I think we need to change a little bit our plan. We had on our schedule Professor GLASHOW. I can't find his ID connected, and therefore I would kindly ask Professor Carlo RUBBIA if he's ready to anticipate his talk now.
We are not going to GLASHOW.
Professor Rubbia, unfortunately, we can't find Professor GLASHOW connected. So if you are kindly ready to anticipate your talk, we would really appreciate that.
Well, so this is how we discuss about experimental searches on neutrino anomalies. Can I get the next picture? So what are neutrino-related anomalies? Several anomalies have been collected for 2 decades in the neutrino sector, suggesting the existence of some additional new related states beyond an ordinary 3-flavor mixing picture. The anti-neutrino electron appearance in the accelerator LSND was the beginning of the story. Reactions in anti-neutrino electron keep going to a positron plus a neutron, with a neutron later captured by a proton, and then a neutron plus a proton will go to the deuterium plus gamma. There's a picture of the anomaly, as you can see. You can see that its signal is significant. There is about 3.8 evidence for oscillation. Another important story about is a story of Seiji galaxy experiment, where the neutrino electron disappearance with a mega Curie sources and observation gave a predictor rate which was less than 1, 0.94 plus or minus 0.05. Next. The anti-neutrino electron disappearance on nearby nuclear reactor experiments again gave a number which was far from 1, 9.34 plus or minus 0.24. And then finally, the recent observation of sterile neutrino oscillations by neutrino 4 experiment, of which I will spend some more time discussing it. Next picture. So the neutrino 4 experiment, the experiment has studied the possible observation of neutrino produced in oscillation by an additional sterile neutrino as a function of L over E, where L being the distance traveled in meters, and E the energy in MeV of an incoming neutrino electron on a proton. Next, 8 meters for the 90 MeV reactor core of 35 times 42 times 42 centimeter cube, one can record about 300 anti-neutrino electron events per day with 1 cubic meter of liquid scintillator. A typical 9-meter distance, the neutrino energy is 9 MeV for L over E equal 1, and 3.6 MeV for L over E equal 2.5. The reaction is fitted according to the following form. An antineutrino going to antineutrino electron equal to 1 minus sine squared 2 theta 1,4 times sine squared of m14 squared L divided by E, where E nu is the antineutrino energy in MeV, L is the distance in meter, m14 squared is the difference in electron volt squared between the square masses of the electron and sterile neutrinos, theta 1,4 is the mixing angle between the electron and sterile neutrino. The pictures you can see here involve the result of the neutrino 4 reactor signal, which you can see here the signal, observed signal, and the predicted signal, so you can see the situation. And then you see a reactor off, which is the same distribution, which you find essentially the distribution is equivalent to a 0. So the signal has disappeared entirely in L over E. Data have been collected for 3 years until June 2019, followed by background measurements until January 2020. There were 720 days of reactor on and 41.7 for 417 days with reactor off, with 87 reactor cycles total. The difference on and off is 223 events per day in the range between 6.5 and 9 meters. The signal of a background ratio is 0.54. The obtained values of the difference between the masses of the electron and neutrino are given here. The mass 1,4 is 7.26 plus or minus 7.25 plus or minus 0.09 electron volt squared. And the angle theta 1,4 parameters, which is a sine 1 squared of theta 2 theta 1,4 equal to 0.26 plus or minus 0.09. Next. The main result, oops, sorry, I cannot see that. The result, this is wrong, it's too small, we cannot see it. Can someone get it better? Okay, the main result is shown here. Oh, it is still missing. Can you see back again the image again? Because one part is missing. Can you go again through? Next. There is effect. Is effect distributed here. It's more in detail. You can see the distribution is a function of sine squared versus the mass squared, electron volt squared. And this is the area 1 sigma, 2 sigma, and 3 sigma, which are plotted in this distribution. Okay. The main background is electron-neutrino signal is antineutrino electron plus proton going to electron plus positron plus neutron, followed by a second delay step with neutron capturing gadolinium. Fast neutron emitted outside the detector in interaction of high energy cosmic ray muons with matter could, around the detector, become the main source of background in this experiment. The fast background is characterized by the presence of capture in gadolinium. You can see here the neutrino event with the diagram corresponding to the process. And you can see on the other side the main background event in which a fast neutron is becoming a proton and goes again to gadolinium signal. In summary, the comparison of the results between neutrino 4 and the previously discussed experiment stereo and prospect are shown. You can see here the distribution again in the terms of delta 1 squared. You can see the distribution neutrino 4 result, and you can see 1 sigma, 2 sigma signals, and you can see the other information, previous information already described as stereo, 90% confidence level, and prospect, 95 confidence levels. And there is an overall agreement around this value corresponding to this value, which is indicated in red. Now, a new powerful detector technique has been initiated by Icarus at the CNGS. You can see here the basic principle of the distribution. You can see the event, how it's recorded in time. There is a drift direction indicated there, and the events are shown. And you can see a minimum ionizing 6,000 electrons per millimeter, and the scintillation light yield, which is 5,000 electrons per millimeter, 128 MeV. The electronic drift distance is 500 volts per centimeter. Drift electron moving to transparent wire arrays oriented in different directions where signal is recorded. Now you can see here the picture of the signal, how the electronics is organized. You can see the preamplifier, shaping amplifiers, memory recorded, and the readout is plotted in the diagram, which you can see here present. Next. Next, please. There is a continuous recording. The characteristic of the experiment is high density, non-destructive readout, continuously sensitive, sense triggering, very good scintillation to 0. Thank you. Next. You can see here the 3 planes of the electron drift, the UTV, the UV, the VTV, and the WTV, which are 2 signals, and then eventually, which are recorded, and then finally the signal is collected at the end of the signal, of the third signal. And the value which indicated here are 500 volts per centimeters. The P is 3 millimeters, D is 3 millimeters, and R is 0.1 millimeters. You can see the figures on the side. Next, at Fermilab, the shallow depth, which is a shallow depth, the T600 will require, of course, 2 additions with respect to the one which was already done in Italy. 3 meters concrete overburden to mitigate the cosmic rays background, and particles entering the detector must be removed with the cosmic ray tagger, CRT, around the full liquid argon volume. Now, here is an example of an Icarus event in which a K plus becomes a mu plus, it goes then to electron plus, the CNGS. You can see the picture to the left. You can see how the K goes to a pi, mu, and then mu goes to the electron in the collection, as represented by the picture. You can see on this other side, next picture, the same distribution in deduction. And you can see how this event can be reconstructed in 3 dimensions. You can see the K coming in, becoming a mu, mu traversing along pathways and eventually ending up to become an electron. Next. Efficient low misidentification due to precise 3D dimension, reconstruction, DDX, range measurements. And next, stopping power, you can see that. And then finally, please, next picture, next point, recognition of secondary particle production of decay. You can see on the right-hand side, the distribution is a function of the range. In the case of a B track, which is a K+, please indicate K+. And then there is the other events, which is a mu also indicated. Please show the two things, the pi, K+, and the mu, which are identified, as you can see, as a function of the DDX. They are very clearly separated. These are the points measured experimentally. Next picture. This momentum, mu momentum via multiple scattering is an important characteristic. In fact, the only thing missing to become a real bubble chamber here is the magnetic field. So there is no magnetic field. The initial momentum may be determined through a reconstruction of multiple Coulomb scattering in liquid argon. You can see the picture. The RMS is shown here. You can see here the angle is a function of the distance. The wobbly track represents the way in which the signal is moving along. Next picture, please. Method is tested on 10⁻³ stopping mu's at CNGS. Neutrino interaction upstream rock, comparing multiple scattering measured by MS with a corresponding calorimeter in the distribution. You see the ratio here, the multiple scattering over calorimetry. And you can see at the end, the distribution of the events, the last events. You can see the initial from calorimeter indicated there in GeV. On the other side, the P measured in the opposite directions. You can see the two values are in fact quite similarly to each other and represent a very good connection, which you obtain by using multiple scattering to identify the event, the energy of the event, which you have observing. Next picture. Sorry, here you can see here the picture at Fermilab. You can see more detail. Please give me more details. You can see the microboon 69 interactive mass. You can see then the next SN-BND with 82 interactive masses. And finally, you can see Icarus, which we wrote described, which contains 476 active masses, all the different distances with respect to the production point of the neutrino at Fermilab. Next picture. Oh, this is lost. This is partial. Let's go on. Now, there are very substantial similarity between the neutrino 4 and Icarus. Icarus, the booster, and the NUMI have a remarkable similarities with neutrino 4. We should be able to settle the neutrino 4 prediction both in the E mu of the booster and within neutrino E with the NUMI. The booster is about 600 meters from the target, can be directly compared to neutrino 4 with a target of 42 centimeters, followed by a detector between 6 and 12 meters, with a neutrino mu collected with 100 times the energy. The number of booster events with 1.6 million microsecond spill, 10⁻12 photon per spill, 5 Hertz repetition rate are 12,800 events a day, of which 7,800 events per day are due to cosmic rays. The NUMI off-axis, the NUMI case, off-axis proton beam, is located at 700 meters at the distance from Icarus at an off-axis angle of 6 degrees. For 1 year, with 0.57 Hertz NUMI repetition rate, a spill of 6 to 13 particle per photon, we expect for sensitive, expect for positive and negative focusing, 4.64 10⁵ CC events per year, and 3.78 10⁵ cosmic rays per events per year. Now, the analysis procedure for the application of the early Icarus data is based before the second detectors are being made available and will occur, roughly speaking, at the end of this year. The proposed research will be limited to observation of the quasi-elastic process charge current in neutrino mu plus neutron going to muon plus proton for booster, and neutrino E for neutron going to electron plus proton for NUMI. Only events with only one very separated sensible PMT fast signal during the duration of the T=0 burst will be retained. Initial automatic event selection is based on the sum of the signals from the PMTs above the threshold and the absence of signal from the CRT over the 4 pi surface, occurring few nanoseconds before, after, or before the earliest of the PMT signal with the event. The event missed by the CRT detection inefficiency also kept. The simple fast signal selection will reduce the amount of 1 order of magnitude of the events initially in excess of 10,000 a day. Next, the 3D 1 millisecond long image will be displayed, and then only for these resulting triggers. The 3D 1 millisecond image is a real image of the event. You can see it here. A connected vertex of 2 pointing track will be searched inside the 1 millisecond image, one for high DDX stopping proton, and the other for a stopping muon from the booster, or a single showering for the NUMI. All other kinds of tracks visible in a 3D 1 millisecond log image escaping events will not be considered. The position of the pattern in the visual 1 millisecond display will consider with one of the PMs only for t equals 0 patterns. This is why the search of pattern in the visual image should cover the full visible area. The kinematics of the finally recorded vertex will be compared with a prediction already described in the Neutrino 4 experiment, confirming the absence of these events for a test sample out of time recorded events. Here you can see the picture of a direction of the proton stopping. You can see the range from the endpoint indicated here as a function of the line you can see there for 10 grams per square centimeter, 100 MeV is indicated. On the other the diagram, you show the MeV in centimeter square per gram, the 10 MeV also marking the stopping power for the endpoint for proton energy, and the minimum ionizing particle is indicated in the corner down there. Next. The search for 1 millisecond display will be started with instrumental detection of endpoint proton D3 tracks with the above features. An observed proton track, one must require an attached muon ionizing track, either the muon for the case of the booster or the electron for NUMI. And no distinction is made here between the on-time and off-time events. The validity to the automatically process will be verified by comparing with some events scanned visually. Now, the next general expectation for the future FP taking, please. Data taking is based on a future and definitive demonstration of the initial events of 2.8 standard deviations, L over E decay pattern already observed by the Neutrino 4 experiment. The main experiment will be primarily dedicated to 4 main observations, which I already briefly mentioned. One is the detection of neutrino mu disappearance in the booster beam with the Icarus detectors. Similar, point 2, similar detection of the neutrino electron disappearing in the mu of axis K beam. 3, comparison between the Icarus at 590 meters and SBN 110 meters, when both will be operating, from the target in the booster beam to test the validity of the 3.1 model and the appearance of the neutrino electron signals. And finally, a confirmation of sterile mass for the effective masses of the light and active neutrinos. The mass of the neutrino electron, which is equal by this formula, may be compared with a future direct experiment, for instance, the next experiment, which is foreseen, which is Catherine. Now, let's get to the booster beam. You can see the distribution in the booster beam is a function of L over E. The Neutrino 4 anomaly, you can see the signal, and you can see the expected signals indicated there. Can I see the next picture? The figure represents the survival oscillation probability in the presence of Neutrino 4 anomaly with the value of the Neutrino 4. The calculations be performed considering a 3 years long run and considering the best fit Neutrino 4 parameters already indicated. And we also here we include only statistical error. You can see how beautiful the signal is predicted to be. Next picture. Now, after 3 months from the beginning, with the condition in which the muon track is longer than 50 centimeters, you can see here the distribution L over E as a function of the neutrino anomaly. You can see already in this particular segment, with few months events, you can have a very clear separate indication or confirmation of the Neutrino 4 result. Can I see, please? You can see here the pictures. And now the additional request for muon length of 60 centimeters for a better identification is also being included in the data. And next, it removes all the neutrino events with electron neutrino less than 300 MeV. It reduces the statistic at low energy, increasing the statistical error at high L over E. Now, the NUMI results are shown next. NUMI results has been generated, here, I think again is also too small, by a for Icarus at the end of the axis, chaos are primarily in the off Numi, leading to a much larger participation of neutrino electron signal, which is the one which has been the only been kept. Notice that the image is too small, it's incorrect, there's something wrong with the data. 1 year an exposure correspond to one CC events every 32 spills for positive events, and 1 event every 4 spills for negative focusing. The ratio is indicated here. Next, possible reasonable fiducial cuts events brings the number of neutrino electrons to about 7,300 per year for positive focusing, sufficient to verify conclusion neutrino 4 observation, as well with the neutrino electron after a few months, the take is already indicated. Numi results continuation, please. Here you can see the picture of the distribution as a function of the energy for the neutrino electron, the antineutrino electron for the positive beam, and the corresponding negative beam. You can see again the neutrino electron and the antineutrino electron plotted in distribution. CC rates at the off neutrino mu axis for 430 tons sensitive area, and this number are left referred to CC spectra for the antineutrino E and positive focusing. Data on the right are for negative focusing. Next. Now, the main purpose of this procedure is a confirmation of the neutrino 4 experiment with Icarus in both neutrino mu and neutrino H channel. Next, the analysis is initiated by the presence of within 1 millisecond visual signal of one higher ionization stopping tracks confirmed to be due to a proton. The line trajectory is reconstructed backwards from its highest ionization point. Next, on the other hand, the proton must be attached either to a muon in one case or a single ionized electron departing at an angle. Next, the activation of CRT trigger and the 3-meter concrete shielding presumed to do not modify the analysis procedure, but only reduce the number of events to be studied. Next, the V is reconstructed in 3 views and 4 contained events. Next, the distribution following neutrino 4 for L of E is plotted with E equal to total energy, as I already said, and L the distance from the neutrino beam, searching for sterile oscillation. Next, you can see here an example of one neutrino going to neutrino E events. You can see the shower being developed, and you can see the very heavy ionizing proton track, also well indicated. This corresponds to an energy neutrino 1.34 GeV and an energy deposited in the picture of 1.29 GeV. And you can see here the feature the radius of the proton is 7 centimeters, and the ratio of the ionization of the proton over the range of the proton is of 13.2 MeV per centimeter. Next event shows the case of a neutrino going into a quasi-electric neutrino mu, CC events going to a proton and a muon. You can see the proton recognized, and you can see the long muon track traveling. And this corresponds to any neutrino of 0.74 GeV. And you can see here the values correspond to a certain conditions, which is a perfectly legitimate, beautiful event. Next. Okay, now this is a distribution of the neutrino mu events as a function of the energy. You can see all the tracks together, please. Here is the muon range, the proton range, and this is distributed. Next, the muon range versus muon angle, and the next one is the proton range versus proton angle. You can see the values are quite sensitive and they're quite well understood and beautiful. Next picture. There is only 1% of the events which you don't see a visible proton in the data. 8% of the event, the proton range is below ½ centimeter, so a very short proton track. Next, transparency. The structure, a 3-point linear representation probability of various oscillation. Can you see the picture here? Next picture, next. This picture I will just show like that. I can skip that thing, the rest of the picture. I can skip the rest of the picture. Thank you. These are predictions which you predict. Now, confirming the 3.1 model joined by Icarus and SPMB. Now, constellation may occur between appearance and disappearance. There is an important difference, however, between the original LSND experiment and the future Fermilab programs. This is due to the fact that neutrino events are now produced from a generated neutrino event and for intrinsic neutrinos added to a intrinsic neutrino sources with about 0.5% of mu, right, which is not present in the original LSND event. Attenuation, analogy in the case of nuclear reactor, must occur also for intrinsic beam produced source. Therefore, cancellation between this and LSND generated neutrino mu, neutrino F conversion are expected to detect the signal, which you indicated here. The combination with the two is as this diagram. Next picture, where, as I already said, delta one square is a square mass difference, and L over E is already described previously. Next. Now you can see here the effect of the various presence, intrinsic plus appearance, intrinsic appearance plus disappearance. You can see that the various distributions are combined, and in fact they can overlap partially, as you see in the next picture. You can see here, these are given for an example of 1.5 electron volt squared. Can I see the next picture? You can see in fact that the distribution can, in a particular cancellation, there could be a complete cancellation between two phenomena because the intrinsic appearance and intrinsic disappearance cancel, giving you a signal which is as if it would completely reduced. Next picture, please. Electron recombination effects is an important question. Next picture, please. None of the electron recombination theories so far is really successful in describing experimental data in liquid argon. Nevertheless, they provide a basis for the understanding of all the phenomenology approaches. You can see from this diagram here, the signal as a function of the, and the reduction due to the combination of effects is substantial. You see that initially, with the higher ionization, the signal is strongly reduced. The combination effect has been already carefully studied and is an important process which needs to be further studied. There are several minor additives in the liquid argon which may modify this effect, transforming some of the produced light into additional ionization, which could be useful also for the future Fermilab program. Can I see the picture? Next picture, please. Next. You can see how we can do, for instance, the result with products because tetrametrine germanium. Can I see next? A possible solution improves the linearity detector response. To introduce a photosensitive dopant able to convert part of the scintillation light into additional free electron ion pairs, thus enhancing the linearity as a function of the deposit energy density in the electron field. We have chosen TMG as a photosensitive dopant because TMG is not absorbed by the recirculation system, can be easily purified. Next, TJ large photoabsorption cross section, which is 62 megabar and an acceptable quantum efficiency. Next, the performance of the detector is greatly improved and is remarkably stable with time. You can see a picture how the thing looks like. Can you see quickly the picture? You can see here with TMG, with pure argon, you can see as a function of the DDX, the distribution, and you can see how the presence of TMG enhances the distribution and linearizes it quite nicely. Next picture. You can see here the 3-ton, this was done in the 3-ton liquid argon TPC, and it's quite constant. It constants the time. You can see that increasing the lapse time in days, the value from 1.3 ppm to 9.5 ppm gives essentially a constant signal to the observation. So it's a very simple system to improve and linearize the signal for the more heavily ionizing proton tracks. Next picture. The other question, important question, is the presence of positive ion in argon. In the shallow depths, ion is content the present intense background due to cosmic ray muons, which have to be separated out of the neutrino signal. This background signal also generates liquid argon positive ions, which flow very slowly with a mobility which is incredibly small, 6.3 10 to the minus 3 centimeter per second per volt. You can see in the picture how the ionizing track is modified because of the presence of the positive ions. You can see the apparent track being displaced with respect to the actual presence of the ionizing track. Next. Next picture. Okay, with the signal is a very long time, it may produce, of course, space-size effects. When I can see, please, next picture. Next. You can see here the effect is a function of drift field. And you can see here that the effect is a function of distance. And what is the effect of this is with the 1.5 meters drift, which you chose, we can see the signal is in delta t in microseconds, still small. But if you have a much longer path, as you can do, for instance, future detectors, the effect becomes quite enormous. Next picture. You can see here the way of solving the problem is to introduce intermediate grids inside the distribution to stabilize. Oh, wait. No, you got lost. Here we are. In fact, adding one grid or 3 grids, you can reduce the signal quite a bit. So, but in the case of a much wider interval of collection of the ions, we have to have grids inserted as wires, which will ensure a stability of the voltage. Next picture. Okay, now, next question is cosmology. And 3 neutrinos give a very small for the sum of neutrino masses. That's all. Quite independent from the outcome of the neutrino 4 experiment, there is very solid information about the possible existence of the sterile neutrino. That Icarus may be able to observe with LOVE of a wide mass ranges, provided, of course, the mass 4 is much greater than mass 1, mass 2, mass 3. Both can be estimated by a simple formula. Next. It's simply due to this is simply due to the fact that the fraction of the effective sterile mass is mixed with the effective masses of the light neutrinos, neutrino E, neutrino mu. So what we see is an effective mass, which has a component which is also coming from the presence of the sterile neutrino. A value has been derived, or 0.59 electron volt has been derived in the case of neutrino 4. Of course, it does not contradict the fact that so far we don't know whether the neutrino Catherine has observed an effect, but he's supposed to see it also in the future, confirm that result. Next picture. You can see here the situation for the various limitation on neutrino masses. You can see how the results are. These are results from neutrino 4, which you would like to reproduce in our experiment, both for neutrino mu, neutrino E, and neutrino tau. Next picture. Conclusion. The problem of neutrino anomalies has been asked for about a quarter of a century. Next. The recent neutrino 4 experiment is a major step forward, however still statistically weak, representing only 2.8 sigma signal. Further analysis is needed. This is why we need the experiment, which you're doing here at Fermilab. The reactivation of the Fermilab booster UV beam is expected by the end of the year 2020, actually 21, followed by initial operation of Icarus in both locations. Definitive eventually confirming evidence for 1 and 2 with the neutrino mu and neutrino E are foreseen after a few months, even before the other experiment, LSND, will come. After approximately the first year of operation, the SNBD liquid argon TPC detector will be added. So it will be a 2 detector at a shorter distance from the booster to perform a definitive 5 sigma analysis of the sterile neutrinos in evidence 3. Next. The evidence, the value of effective light neutrino masses because of the presence in the combination with the sterile neutrino is calculated as evidence 4. Thank you very much. How much time did I have?
Thank you, Professor Rubbia. It was, as usual, an honor to have you at the Neutrino Conference. And with the same honor, I will introduce you now, Professor Sheldon GLASHOW.
GLASHOW is coming. Very good. Sheldon.
Hi.
Hi,
Carlo.
Good seeing you.
Good seeing you.
Welcome,
okay.
Welcome, Professor Sheldon. Just one apology. I mean, the new technologies help us a lot, but sometimes can be diabolics. So I'm sorry if you had to wait a little bit longer. Thank you, Professor.
Thank you so much. It truly is an honor to have the opportunity to give the, I thought it was going to be the opening, but Carlo beat me to it, opening talk at the 19th edition of this wonderful workshop on neutrino telescopes, of which, by the way, this is the 4th workshop I've been privileged to attend. My earlier experiences were all instructive, enjoyable, and graciously hosted by Mila Baldocciolin. They took place in Venice, mostly on dry land, but partly on water when Venice was flooded. This time, for a change, our proceedings are on air. Neutrino physics has begun its vigorous 9th decade with Miller's dream of neutrino astronomy now fully realized. Today, I shall, unlike Carlo, give no slides, no pictures, no graphs, no equations, and no theoretical insights. Instead, my talk begins with a timeline of our enchanting discipline, mentioning some highlights with which my younger listeners might not be familiar. Please forgive me the many errors, omissions, and the indelicacies of an elder but not necessarily wiser colleague. We begin in 1930 with Pauli, who chose not to travel to a physics conference, sensibly opting for a Christmas ball in Zurich instead. In his letter of apology to the assembled radioactive Damen und Herren in Tübingen, he described his desperate remedy for the vexing problem of the continuity of the beta spectrum, and he dared to propose the existence of a new light and neutral particle to solve both the energy problem and the statistics problem. 3 years later, Enrico Fermi dubbed Pauli's putative particles neutrinos. He put them and their antiparticles to very good use in his theory of weak interactions. And now we jump to 1946, behind the Iron Curtain, where Bruno Pontecorvo proposed the radioactive chlorine experiment that would later be used by Ray Davis to study, observe and study solar neutrinos. Ray's null experiment in 1955 at the Savannah River nuclear reactor showed neutrinos and antineutrinos to be different particles. 1 year later, also at the reactor, Clyde Cowan and Fred Reines triumphantly detected reactor neutrinos. Pauli was delighted, as was every physicist then of a certain age. In that same year, Madame Wu, following the counsel of her Columbia colleague, T.D. Lee, was the first to show that weak interactions violate a parity or mirror symmetry, and that neutrinos are left-handed. An American postage stamp with a flattering image of her has just been issued. 1957, my thesis advisor, Julian Schwinger, proposed that a triplet of vector bosons could mediate both the weak and electromagnetic interactions. He was kind enough to leave the details for me to work out. Furthermore, the V-A theory was devised by Sudarshan and Marshak, and an identical theory was proposed, not quite independently, by Feynman and Gelman. Later in 1957, for the sake of the record, Sid Bloodman suggested the first gauge theory of the weak interactions, just as John Sakurai had done for the strong. Neither of these precocious gauge theories would long survive. 1958, my high school buddy, Gary Feinberg, assuming weak interactions to be mediated by vector bosons, showed why the observed absence of radiative muon decay, still unobserved, demands electron and muon neutrinos to be distinct particles. During my thesis exam that summer in Madison, Wisconsin, C.N. Yang, a member of my exam committee, learned from Schwinger how it is that electron and muon neutrinos, if they were different from one another, could be experimentally distinguished by experiments. That was 58. In 1960, I proposed a gauge group SU2 cross U1 to underlie electroweak forces. That predicted neutral currents, but neutral currents of an entirely unsatisfactory nature. The Jim mechanism would undo the damage almost a decade later. 1962, my late friends Leon Lederman, Mel Schwartz, and Jack Steinberger, with a brilliant experiment, designed and performed the experiment to prove that muon and electron neutrinos are distinct particles. 1966, Sterling Colgate and Richard White deduced that about 99% of the energy released by a core collapse supernova is emitted as a brief but intense burst of neutrinos, such as would be observed 21 years later. 1968, John Bicol and Ray Davis, a theorist and an experimenter, uncovered a puzzling deficit in the observed flux of solar neutrinos. Was it due to a flaw in Bacol's solar model or a systematic error in Davis' experiment? Or did neutrino flavors oscillate, as Pontecorvo first suggested? The solar neutrino problem would challenge physicists for decades. 1972 to 1974, neutrino action, excuse me, neutrino interactions studied at Gargamel confirmed that quarks have fractional charge. They also discovered the neutral current interactions that had been predicted by the electroweak theory. Fermilab would soon confirm the dramatic discovery. 1975, Samios group at Brookhaven claimed to have discovered the first charm particle, a baryon, produced by a neutrino impact whose measured mass lay very close both to its actual value and its predicted value. 1 year later, charmed mesons aplenty were seen and described at SLAC. 1979, Larry Sulak and his friends conceived, designed, and created the first massive underground imaging water Cherenkov detector. Such devices have enabled the spectacular achievements of IMB, Kamiokande, Antares, Super K, Camland, IceCube, and SNOLAB, as well as those of future facilities such as Hyper-Kamiokande. 1987, an intense neutrino burst from a relatively nearby supernova was observed by IMB in Ohio, Kamiokande in Japan, and by the Baksan Neutrino Observatory in Russia, thus confirming our understanding of supernovae. Later on, the event was seen in visible light, X-rays, and gamma rays, thereby initiating the notion of multi-messenger neutrino astronomy, about which we'll hear a lot more at this meeting. 1988, from its studies of Z0 decays, CERN measured the number of active neutrino species to be 3 to within 0.2%, in excellent agreement with astrophysical estimates and, more importantly, with nature. We'll see what happens with sterile neutrinos, or seemingly sterile neutrinos. 1997, Fermilab's donut experiment managed to detect the interactions of tau neutrinos, whose existence, however, no one had doubted. 1998, Super K published a neutrino image of the sun, but much more importantly was its astonishing but anticipated discovery of atmospheric neutrino oscillations. I was there, and that proved that neutrinos have mass. Announced at the Takayama 1998 Neutrino Conference, the work earned a standing ovation, which doesn't often happen at physics conferences. 2001, Sudbury Neutrino Observatory in Canada ingeniously measured the fluxes of solar neutrinos of all flavors. Along with Super K data, their result confirmed the standard solar model, and the decades-old solar neutrino problem had finally been put to rest. We jump to 2012, the Daya Bay and Reno experiments in China and South Korea finally managed to measure theta 3.1, the third of the four angles of the Pantriagan-Maki-Nakagawa-Sakata neutrino mass matrix, which I must say is a rather mysterious multiple eponym, but one that may need revision if the not quite sterile electron volt scale neutrinos, such as my dear friend Carlo was discussing, are found to really exist. 2017, at the South Pole, the IceCube Observatory detection of a high-energy cosmic ray neutrino triggered other observers to detect gamma rays and other electromagnetic signals from a blazar. IceCube had located the first known source of cosmic rays and high-energy neutrinos. IceCube came in again in 2019. IceCube detected one likely instance of the so-called GLASHOW resonance, which I imagined over 60 years ago in Copenhagen. Let them see another. 2020, Hyper-K was approved for construction by the Japanese government. Meanwhile, the T2K experiment severely constrained the CP violating phase of the PMNS matrix. The absence of CP violation amongst neutrinos was excluded at the 95% confidence level, very much encouraging further neutrino experimenters. 2021, we're getting to the end of our brief review of neutrino physics of the past. At least 12 electron volt scale, maybe 13 with Carlo, sterile neutrino searches are underway in Antarctica, Asia, Russia, Western Europe, and the United States. As a result of this surge of interest in sterile neutrinos, wrote the CERN Courier, detector technology has improved to the point that they may be used to monitor nuclear reactors. With this reminder that even the least practical pursuits of us particle physicists, that even these most absurdly impractical pursuits can be of benefit to society. And thus we reach the end of our timeline. Let's turn to the future of neutrino physics if I have any time left. Why has there been such fervid interest in the possible existence of hypothetical spin-a-half neutral fermions, also known as sterile neutrinos? While only 3 active neutrino states participate in the standard theory, several sensible arguments suggest the existence of additional sterile or quasi-sterile neutrino states. To wit, 1, right-handed neutrino states are needed if standard model neutrinos are to be Dirac fermions. Neutrino masses would then be lepton number conserving, and the mechanism for neutrinoless double beta decay would be totally disabled. However, these are not the sterile neutrino states that interest my experimental colleagues, nor do we know how we can search for them directly. 2, quasi-sterile neutrinos with large Majorana masses, large indeed, and small mixings with active neutrinos are essential to implement the most popular mechanism for generating neutrino masses, the seesaw mechanism. But neither are these these are also not the EV scale neutrino states being sought, although as a side issue, their decays might provide interesting targets for the LHC, or they may prove to be cosmologically significant. 3, what actually motivates all these searches for EV neutrinos, EV scale quasi-sterile neutrinos? I say quasi-sterile because they're not sterile. They must interact, they must have mass and mix with the active neutrinos if they're to have any useful effect in explaining the several otherwise inexplicable quote unquote anomalies reported by LSND, Mini Boom, GALAX, SAGE, as well as various shortfalls and bumps in the measured fluxes of reactor antineutrinos. Now, I have to say that we may search for them at our pleasure, but EV scale quasi-sterile neutrinos have no known theoretical raison d'etre, and experimental anomalies are often otherwise explained. So I'm not yet convinced by Carlo that I don't yet believe that sterile neutrinos have been shown to exist. Several substantive questions remain about our 3 known neutrino states. We know a lot about their squared mass differences, but we don't yet know their actual masses. Astrophysicists, if we're willing to believe them, have set upper bounds on the sum of their masses, which they say cannot exceed about 120 millielectron volts. On the other hand, we know that their sum must exceed 60 millielectron volts for the normal hierarchy, or 100 millielectron volts for the inverted hierarchy. The squeeze is on, with the astrophysical constraint likely to tighten. We shall soon learn which hierarchy nature favors. Equally important is delta, the measure of CP violation in the neutrino sector, which T2K, as I mentioned, has recently constrained but not measured. I expect that that challenge to measure delta shall also soon be met. Are neutrino masses Dirac, Majorana, or a bit of both? They would be Majorana if neutrinoless double beta decay were detected. This beyond the standard model lepton number violating process was first discussed back in 1939 by my erstwhile Harvard colleague, Wendell Furry. Ever more sensitive but always fruitless experiments for this rare or perhaps forbidden decay mode have been made. The most sensitive, I thought, was the Japanese-American-French collaboration Camlan-Zen, who claimed, I think, that the neutrinoless beta decay, double beta decay lifetime for xenon 136 exceeded 10 to the 26 years, and the EE entry of the neutrino mass matrix had to be less than about 100 millielectron volts, in concord with astrophysical constraints. Future experiments will target lifetime limits as much as 100 times greater, or better yet, they may result in the dramatic discovery of lepton number violation. Let's hope that comes to pass. 3 ambitious and costly research facilities are to be completed this decade. The Juno underground neutrino experiment in China, Hyper-K to be hosted in Japan, and the deep underground neutrino experiment, DUNE, to be sited at Fermilab and at Sanford Lab in the United States. All 3 facilities will be international, involving scientists from at least 39 different countries and counting. You will hear much more about them in the next few days, I'm sure. It's likely, to me, that experiments there and elsewhere may deal with all of the issues I have mentioned, hopefully posing new puzzles as well. However, I believe that the grandest challenge for both neutrino experimenters and neutrino theorists is to ask and answer those questions about neutrinos that we have not yet been imaginative enough to think of. Surely there will be many more exciting discoveries in neutrino physics, and there will also be many more workshops on neutrino telescopes to discuss them. Hopefully, there will take place in La Serendissima di Venezia, whether it is flooded or not. Thank you all for your kind attention.
You, Professor GLASHOW. Apologies again for the misunderstood before. And now it was, of course, an honor to have you at the Neutrino and the Neutrino Telescopes Conference. Now, with the same honor, I'm proud to pass over to the Professor BARISH, another Nobel Prize, who honored us of his presence. To you.
Hi, let me try to share my screen and then I can start. Okay, I assume you can see the screen now.
Yes, we can see.
Okay, first let me say that I'm honored to be on the stage this morning. For me, it's actually just turning light in California with my good friend Shelley GLASHOW and Carlo RUBBIA. We heard 2 different views of neutrino physics. I've been coming to Venice for many, many years, and I'm very happy to participate again, and very sorry that I'm doing it from California instead of from the beautiful location and party and place in Venice. As you might guess, I'm going to talk about gravitational waves today, which is not neutrinos, but I'm going to point to the aspect of it that I think, maybe in the spirit of the end of Shelley's talk, is a future where neutrinos will play a big role in astrophysics and cosmology when we begin to connect the information from gravitational waves, from astronomy and astrophysics itself, and from neutrinos. I show over on the left the first glimpse of that we have from gravitational waves already, and I'm going to talk about it, which is a coincidence of being able to see a signal in gravitational waves and in astronomy at the same time that yielded a huge amount of information on physics, not just accomplishing that you see a joint signal. This is a signal that I'll talk about in a while, which came from a neutron star merger about 150 million light years from the Earth. And the signal on the bottom is the colored one is a time frequency signal of the gravitational waves, the line going to higher frequency as the signal emerges. And the ones on the top are the light curve seen from a satellite, seeing the high energy gamma rays that came from a merger. Just to point out one piece of physics immediately that is evident to anyone looking at this graph is that the two signals came within 2 seconds of each other. That's within 2 seconds out of 150 million light years, which means that you can immediately conclude that gravitational waves, as predicted by Einstein, by the way, that gravitational waves and neutrinos both travel at the same speed, we call it the speed of light, to 2 parts in 10 to the 15. So that's 150 million light years. So that's a pretty good proof already, without me going any further, of a measurement that came immediately from doing a coincidence measurement between an astrophysical measurement and a measurement with gravitational waves. Of course, we expect the signal from optical signal, which came from gamma rays, to be later than the gravitational wave signal. So even the 2 seconds is expected. We expect that in the collision of neutron stars, the gravitational effects are first, and then followed by the nuclear physics, which emits the gamma rays. So we don't know how much that time will be, but it's small compared to 10 to the 15 seconds. So I'm going to talk a little about gravitational waves, pointing toward the time when we'll be able to also include neutrinos in this. I think the speaker that'll follow me, Francis HALZEN, we'll talk about the largest neutrino detector presently exists, will hopefully talk a little bit about how neutrinos can be part of this new field, which I think will emerge in the next decade of multi-messenger astronomy. First, a little about gravitational waves. So we expect, just pictorially, as I say, that the multiple information from electromagnetic probes, measuring a lot of details about something that happens in our universe, information from gravitational waves and from large neutrino detectors will combine to be used in this next decade, I hope, or maybe even sooner. First, gravitational waves. Let me remind you that gravitational waves are a consequence of special relativity. They were put forward by Einstein in 1915 when he brought the theory of general relativity forward a year later by looking at the equations that he was getting out of a similarity in the equations that he was getting in general relativity to electromagnetism. He made the leap that there must be gravitational waves. It was many decades of people doubting it and believing in it before theorists agreed in the late 1950s that gravitational waves indeed exist in the theory of general relativity. And the search to finally see them took another 50 years or more. So basically, gravitational waves, as we saw in the previous slide, travel at the speed of light. They're made by, in this picture I had here, they're made by not a dipole moment like electromagnetism, but a quadrupole moment. That was also shown by Einstein in 1918, that it's a quadrupole moment. And an example of a quadrupole moment is two stars or objects compact objects going around each other and eventually merging. And then that makes a quadrupole moment. There are many different sources that already we know that exist that should make detectable gravitational waves. I list the main categories here: that chirps, which is what we've seen, which can come from the merger of compact objects. The first ones we saw were the mergers of two black holes. There's also the merger of neutron stars, which I just saw, which is the second observation we've made. And the primary method that we use to see those is what we call matched templates. That is, we calculate with general relativity what the waveform will look like, and we match it to what we see, and vary the parameters of general relativity to determine the parameters of the merger. A second one, and maybe a very prime one to hope that we see detections in both gravitational waves and astrophysics, but also in neutrinos, is the collapse of a star, a supernova. And that, of course, we don't know when we'll see one close enough to the Earth to be able to detect them, but that is a prime place where we can study first the collapse itself from gravitation, then the nuclear physics when it merges, and finally the optical signal that comes out, and learn really what a supernova is like in the future. Another one, which is quite different, and if I had to guess what will be the next observation that we'll make with gravitational waves, are sources that are periodic. An example of that is just spinning neutron stars in our own galaxy. To the extent that they're not perfectly spherical, they'll have a quadrupole moment. And that quadrupole moment then gives gravitational waves. This has the advantage, once we see them, that they're not episodic. They're not just a burst or a signal that's come and we study what we can study and they're gone like the black hole mergers. But instead we'll be able, once we identify one, to be able to study it in more and more detail, even if it means taking long observations or improving our detectors. The understanding of what a neutron star is really quite vague at this point and not constrained by experiment. Lastly, and most exciting probably, are signals from the early universe, the stochastic background from the early universe. We look for that now. We haven't seen it yet. We're working at very high frequencies, and it may be that working at somewhat lower frequencies will be necessary to see the cosmological signals. So that's kind of a sweep through what we see as the physics. Just to illustrate that general relativity produces waves, I write here a simple form of using general relativity of what the equation looks like. And I show what it is on the left, but only to show that it looks very much like the wave equation. So the fact that gravitational waves and electromagnetic waves have a similar form is obvious if you kind of set up general relativity as I have here. Then from that, it's clear that you'll expect plane waves, and that's what we detect. The strength of those waves is the little h in my equation above, h mu nu. And the only difference is that gravity is spin 2 instead of spin 1, so that the two waves are 45 degrees from each other instead of 90 degrees from each other, like in electromagnetism. And so far, we haven't been able to have good enough data to break apart those two, or even show that there's two polarizations. But that'll, I think, happen in the next few years. We need 3 detectors to do that. And so we awaited because the 2 American detectors are oriented at the same orientation to each other except for the curvature of the Earth. So it meant adding the Italian detector, Virgo, and as the data gets better, especially from Virgo, we'll be able to separate the polarizations in gravitational waves. So the detection itself is that comes from the fact that when gravitational waves go through space, they distort space itself. So at least in general relativity, it's not like electromagnetism that they're accompanied by a photon, or in this case, a graviton. In classical general relativity, they're just distortions of moving at the speed of light, of course, of space itself, and distortions in space and time. And the strength of it is this little h that I gave. The strength of it for the source that I'll show, the sources that we're detecting now, is about 10 to the minus 21. That's that little h, the size of it. And it's what makes it experimentally so difficult to measure. What that translates to is if I had a circle like I illustrate here, free masses and a radius L, the distortion would make the circle into an ellipse. It would go from a vertical ellipse to a more horizontal ellipse at the frequency of the gravitational wave. And the size of the distortion is 1 part in 10 to the 21. That's much smaller than the size of a proton, of course. If I had the circle of a meter, 10 to the minus 21 meters, and that immediately tells you why when we build a gravitational wave detector, we make it kilometers instead of meters. And that means the size that we have to measure, which is still incredibly small, is 10 to the minus 18 meters approximately in the detectors that we've built. So that's the background. We use interferometric techniques to measure gravitational waves. That's shown in this illustration, where a laser beam comes in and splits and goes down 2 arms perpendicular to each other. If a gravitational wave goes through the picture that I've shown here, then just like I showed before, it'll distort the vertical and horizontal such that the time to go horizontally and vertically bounce back off a mirror and come back is the phase changes a little bit, and we sense it in our detectors. In order to do that, without going through any details, well, there's 2 experimental challenges oversimplifying things. One is that those of you that have done interferometry probably saw fringes in an interferometer in the laboratory, and you can tell how far apart those fringes are to some fraction of a fringe. Maybe if you're really good, 100th or something, but we have to do that to 1 part in 10 to the 12th. And that's the optics of the interferometer itself, and what took so long in terms of finding enough ways to make an interferometer that was accurate enough to be able to split a fringe to 1 part in 10 to the 12th. The second experimental problem is that we live on the Earth, and the Earth shakes too much. So we can't make an interferometer that's that good. So in a sense, we live on the Earth, but we have to float the detector over the Earth. That's not easy. Almost anything you do is basically connected to the Earth still. And so we basically have to do that with experimental techniques, and again, to an incredible accuracy. And that was the final challenge that we had to beat before we detected gravitational waves. We have to isolate ourselves from the Earth with everything in the interferometer, from the laser to the mirrors, to 1 part in 10 to the 12th. So those are the 2 experimental challenges. I won't go through what it took to do that, but those are the 2 experimental challenges that took so long, but now we know how to do that and even do it much better. LIGO itself is 2 detectors. We have a 3rd one now in Italy, Virgo. The 2 detectors in the US are 3,000 kilometers apart. Being 3,000 kilometers apart, with the speed of light, if a gravitational wave enters from the northeast, where the detector is in the state of Washington, and then goes to Livingston, Louisiana, where our 2nd detector is, the difference in time of the 2 signals would be 10 milliseconds. If it came the opposite direction, it would be 10 milliseconds the other way. And of course, anything that bisected the two would be in between. So we do the classical problem of basically requiring a coincidence between the two detectors to determine gravitational waves. That coincidence is done to plus or minus 10 milliseconds. So we look at off coincidence times to measure how much background or accidental events we have. And that generally can tell us what the probability is of any signal we have being real compared to any background. That's directly done by measuring the off coincidence signals. This is two pictures of LIGO. They're identical, the two instruments. Every time we change a circuit in Hanford, Washington, we propagate the same change through the circuits in Livingston so that we keep the two detectors, which of course being sophisticated detectors, there's always changes being made, but keep them as identical as we possibly can. With that in mind, it turns out that when you look at LIGO data, you'll see that except for a few times where we didn't do the upgrades and bring them to completion at exactly the same time, they give the same sensitivity, as well as you can see on the graphs that we present. So these are 4 kilometers long, and it's an interferometer with the sophistication to get the 10 to the minus 12 that I mentioned, both in terms of the interferometry itself and 10 to the minus 12 in terms of how well it floats above the ground. This was the initial detection of gravitational waves, which I prefer the picture on the right. The picture on the right on the top is the signal in Hanford on the upper left, and the signal in Livingston on the to the right of that. And to the eyeball, they look pretty much the same. They're a little wiggly. That's our measurement errors. On the second panel is the calculations from general relativity of Einstein for the merger of two black holes with the parameters that I've given, that we gave in the first paper, which is roughly 30 solar mass black holes merging to make a final one that's about 60 solar masses and emitting a couple solar masses worth of gravitational radiation. I prefer this picture because nothing's been done to this. It's raw data basically in the top. It's Einstein's equations in the second, and then I do nothing more than subtract one from the other in the third pane, and you see the wiggles back and forth, which are all experimental noise, with no indication of anything that would deviate in the shape of this waveform that's calculated from Einstein's equations. That waveform starts when the objects are further apart at low frequency, and you can see it get to higher frequency as the merger finally happens and when they coalesce. And that's done for all the signals. This was actually the first one, the discovery of gravitational waves. You can take that waveform, which is calculated, and it has a particular form. This is the chirp mass form that I've written. It has a second term, which I've left out here. And from that, you can determine the masses, the spins, even the redshift, the amplitude, the polarizations, everything you need to tell the parameters, even from a single event. And so the waveform is if measured well, is a very powerful way to analyze the events that happen. We even can tell the precession. And in the later events, the first ones we couldn't see, the later events we're able to do that. And we have information now on the spins of the initial black holes that we've detected. We also can tell the sky location, the distance, and so forth. So the information is, even though the number of events we're getting is very, very powerful in testing everything from general relativity to learning about astrophysical phenomena like the neutron star black merger that I talked about. The sensitive area that we have on the Earth's surface is basically the audio band. We don't do anything audio. It's just that our ears, through evolution, have learned where the Earth is quietest. So we listen where there isn't too much noise around. And so that happens to be a frequency band that's quiet on the Earth. We don't do anything audio, but we're basically sensitive to the same frequency bands. I show here what limits an interferometer. It's useful to see it's simple. And as we go to the future, you kind of know what you have to deal with. At the lowest frequencies, the Earth shakes incredibly. And so we have to cut ourselves off at low frequencies. That's seismic in the picture that I drew here. And it falls like frequency to the fourth power. It is incredibly high at a few hertz. And it's why we don't hear low frequencies with our ears. It would be too noisy. But the Earth is shaking. At the highest frequencies, we're limited by how the statistics of sampling the signal that we see. In particle physics, you'd call that photostatistics. In interferometry, people call it shot noise. So basically, we're limited by shot noise in the middle. And in between, we're limited by basically the fact that we're presently working at room temperature, and that's thermal noise. The thermal noise for us is in the suspension system that we're using to hold the mirrors themselves, and that's what limits us. The shaded area is then where we're sensitive. You can see it's at frequencies from tens of hertz to 10,000 hertz, the audio band. And that the sensitivity, if you look on the left, is the little h that I talked about for gravitational waves, something like 10 to the minus 21 or 10 to the minus 22. I show below all the lines that come from everything that's limiting us at the present time, from how well the vacuum is, to the fact that we work at room temperature, to the fact that if we have enough photons, we have radiation pressure and so forth. The sensitive area is the shaded area. Notice, though, that everything below is technical. That's in contrast to, say, moving past the discovery of the Higgs boson at CERN. So when in discovering the Higgs boson at CERN, we all are very aware that it was a very small little bump. You had to get resolutions good enough over a physics background, one that we can simulate very well, one that we know quite well and have to know very well from previous measurements, but it's physics. So there's no way to eliminate it. You can always only deal with it. The reason why we've been able to move so quickly from initial detections to hundreds of detections now of gravitational waves and other kinds of gravitational waves, and we'll move quickly in the years ahead, is that all the limitations presently are technical, not anything scientific, not physics. So as long as we don't have physics limiting us, all we have to do is solve the technical problems and do better at it, which we know how to do. For example, we're limited by, I call it thermal noise here, and we don't know how we're going to do it yet, but lowering the temperature of the device to cryogenic temperatures will help solve that problem. It's difficult because we have to make optics that'll work cryogenically and so forth. Again, shot noise, we need more photons. And seismic noise, isolating ourselves better from the Earth. These are technical problems, not physics problems. And it's the reason why each time we run LIGO, we turn it off for a while, make very much improvements, and we turn on and we're better. And that's solving these problems, which are technical. So it's for an experimental physicist, it's a very wonderful situation. This is just an illustration of us improving the sensitivity to look like the shape that I have here, by running it, understanding what limits us, and doing various things to cure it over a period of years. So that was basically getting to design. You can see it in the event rate here. This is the event rate for a black hole coalescences. We call our runs observational runs, being like astronomers. Observational 1 was where we detected gravitational waves for the first time and then saw a confirming event a few months later, and finally a third one, and we analyzed the data. The second run, we made some improvements and basically saw 8 events. So we improved ourselves a factor of 2 or 3. The next run, which had 6 months or a year off, we improved almost a factor of 10 and saw 56 events. That's in a year. So we're now at a level where we're seeing 1 gravitational event a week. We were turned off by the pandemic last year, and we turned on When we turn on next year, we should be at 1 event a day. So 1 event is the number of events, but it means also other classes of events will be more accessible than just the black hole events that I talked about. We now have accumulated a large number of black holes. I show them here. The left scale is the mass, and these are all not what astronomers believed you would see, and that is the black holes are quite heavy. They're tens of solar masses, even over 100. And that's hard to reconcile with them coming from a progenitor stars, because heavy stars aren't very stable. So this was the observation. We're now, I'm not going to show you this, we're now looking at, like you do in particle physics, distributions of the distances, the masses, the spins, all the parameters, trying to understand what the origin is of these heavy black holes. Is the origin from some, from progenitor stars? Is the origin somehow from maybe primordial and have something to do with the dark matter? Or is it dynamical, where smaller black holes are eating up other ones and growing to bigger and bigger ones? That's unknown at this point, and measuring the different distributions, the spins and so forth, we're trying to get handles on that. So that's the science we're doing with a larger number of black holes. The second thing that's happening with a larger number is that we're able to go back toward more cosmological distances as the sensitivity improves. And so a big subject that I believe will be the future of gravitational waves in the future is to be doing cosmology with gravitational waves and not just astrophysics. This picture here is the time evolution of a series of black holes, but I show on the very bottom right the binary neutron star one that I showed. Because neutron stars are so much smaller, lighter mass, they go to very much higher frequencies, and they stay in our frequency band for much longer. So all the black holes that we see are tenths of a second, a few tenths of a second of signal, seeing those wheels back and forth in the merger. On the lower right-hand corner, it goes for tens of seconds or even minutes that a neutron star gives a long signal that we detect in our apparatus. So they don't look anything like each other. They're in the apparatus for, as I said, a long time. The problem we have, and not a simple one, is that it's not easy to identify that we've seen gravitational waves. And yet we want to do multi-wave astronomy, coincident wavelength astronomy. That means that when we see something, we need to identify where it is in the universe and quickly tell astronomers where it is so they can point their objects. We did that for the neutron star one that was on my lead graph. The problem is amazingly difficult because obviously it's tough to detect gravitational waves, but we have to be able to tell astronomers with some confidence that we've seen something that they should stop what they're doing and turn their telescopes or whatever their device is and look at a certain place in the sky. We need to be able to tell where it is and have confidence what it is within, a few minutes. That's pretty big challenge for us. And clearly, if we just send them signals and then we say, oops, it really wasn't a gravitational wave, they'll lose confidence in turning. So it has to be roughly 80 or 90% likely. And we've done a lot of work to be able to do this very quickly in an online analysis. Other than doing the identification of the events, we have to tell where they are. We do that by measuring it in different parts of the Earth. We presently have the 2 detectors that I told you in the US and 1 in Europe, Virgo, and we'll have 2 more within the next few years. 1 in Japan, Kagra, which is actually being built and made to work in the Kamioka mine, the same place as the neutrino detector, and 1 in India, which is the Americans are building. We're building as a 3rd LIGO device in India. This gives us enough global coverage so that I've just shown in the illustration here in the size of the little circles, the little ellipses, how well we can tell where an object is in the sky presently. That's the upper left-hand picture of the Earth. And by about 2025, when we have all the detectors working, in the lower right-hand corner. The lower right-hand one corresponds to accuracies of tens of square degrees, which is what you need to tell an astronomer where to look in the sky. Presently, unless we're lucky, and we were for that neutron star event, that we might be hundreds or even 1,000 square degrees. This illustrates that. This is the picture. The big bands are how well we could tell the early events before we got information from Virgo in Italy on events, the earlier black hole observations. Once we detected one in coincidence with Virgo, we got the signal, determined the direction in what's called GW 170814. That's the date. And that is tens of square degrees, 60 square degrees, which is much better. At that point, astronomers are willing to point and look at something. That happened fortuitously just a little before we made the observation of the black hole, of the neutron star merger, which I show here more or less pictorially, that it was detected 3 places in the Earth. We could tell then where it was in the sky. That picture in the sky of where it was is shown here. The LIGO and Virgo picture was shown, and then the bigger one seen from the Fermi satellite. The satellites also could identify where the galaxy was that it came from. That was identified. Once that was identified and we knew how far away it was, the gravitational wave information from this single event, I won't go through how you do that today, gave us an totally independent measurement of the Hubble constant. And that we've published. And in the future, if it remains a controversy over the Hubble constant, which presently there is, the completely independent way of measuring it is with gravitational waves in the way we've already done. But one event doesn't do it accurately enough to resolve that. This merger then was studied with all kinds of telescopes. First was the high energy gamma rays, but then it was studied with short gamma ray bursts, with optical, X-rays, radio, and they come as the signal changes from blue to red. And it's measured over some period of time, and the intensity, it could be compared with models of neutron star mergers and fit what I write here as the kilonova picture. So the kilonova picture is the phenomenological picture that is in the literature that fit very well to what happened in this neutron star merger. A byproduct of that, this is just the picture of kind of the as a function of days, in different colors, how the signal from that emerged. One conclusion that's interesting is that we've never really understood how heavy elements got into the Earth when the Earth was formed. We know that in supernova, we have the fusion process, which dominates. And so we can make all the elements in stars when they make a supernova up to maybe iron. But to make heavier elements in that somehow were there to form the Earth has always been somewhat of a puzzle. Nuclear physicists attribute it vaguely to something called the R process, which has always been hard to reconcile with basically the supernova. It turns out that the merger of two neutron stars, is probably now, although we are judging that from one event at this point, the source of the heavy elements like platinum and gold. And the kilonova process, through, again, the R process, produces heavy elements like platinum and gold and so forth. So past neutron star mergers appear now to be the most likely way that heavy elements were made. And by the way, maybe isn't a surprise, because if you ask how we've populated the periodic table, it's usually done, I'm being a little crude, by using neutrons hitting something heavy, a heavy element, and then making a heavier one, and then naming it something in these tables. So they were made on the Earth, but they were made in the lab, but how they got there in the Earth was from that. Our present focus, in addition to the looking to see the set of, say, black hole mergers to understand their origin, and working toward trying to understand any cosmological effects, is looking at the kind of, in the spirit of what we've always done in particle physics, what we're calling exceptional events. So we now have roughly 100 illustrations of gravitational waves, and some of them, maybe not surprisingly, look funny, and we don't know whether they'll stand up. I'll just show you a couple of illustrations. We're not drawing conclusions yet. First, neutron stars are roughly 1.4 times the mass of the sun. And so the measurements that we have of a binary neutron star, like the one that I showed, is a total mass for the merged object of 2.75 to 2.8. And you'll see that we see an event which we've labeled GW 190425. This is our label. It's 3 1/4, 5 sigma away. And it's in a region that's too light to be a black hole, we think, because black holes, if they're too light, lower than a single black hole, lower than, say, 3 solar masses, don't have enough gravity to be a black hole. So we have events, this is one example, and we have a second one as well, that fall in between. Is that real? Is it our problem? We don't know yet because it's a single event. We also have at least one event with a very large mass ratio. That is, the two objects aren't nearly the same mass, but they're very asymmetrical between each other. This one I'm showing you is a factor of 10. That's a very, very good for testing things like, first, the dynamics, what they are physically, and, for example, numerical relativity, which doesn't really work very well when the mass differences are very different. We also have very, very heavy ones. We don't know what they are. This is an example of the heaviest merger that we've seen. It doesn't look like that picture of a chirp signal that I showed you, but it's not going to, because we can't go to low enough frequency to see a really heavy one, except for the final merger. So this is the signal that we see that looks very much alike in 3 detectors, the 2 American ones and the Italian one. The Italian detector's not as sensitive, so it's yet at this stage. And so the signal looks smaller there, but there's 3 detectors. That could be from very heavy black hole, but they're not supposed to be that heavy. Or it could be other kinds of effects, which I list here. So this is the focus that we have at the present time. This heaviest merger that we have has a final mass of 142 solar masses. That's in a region where people wonder whether there are black holes somewhere between black holes that are created by stellar collapse and super heavy black holes that are seen in the center of, for example, our galaxy. And so black holes in the regions of hundreds of solar masses, we don't know if they exist or whether they've been seen. We've seen now one that I show here. It's a merger of 2 very heavy black holes themselves, 166, 185 times the mass of our sun, making a final mass of 142 solar masses. So out of the roughly 100 events, a handful of those are looking different. We only have one case so far, and it's maybe not very well established, where any of the black hole events have even a hint of an electromagnetic signal that comes with them. There's one measurement on this particular event, but it's not clear whether that's true. Just to end, let me say that this, although the time scale will be long, because of the fact that we're not limited, because of the fact that we're limited by technology and not by physics, we can envision how to make much more sensitive detectors. And in fact, there's 2 rather different approaches, one in Europe and one in the US right now, because we're just figuring out how to do it. But I picked the European one here called the Einstein Telescope, just because there's a list of the kinds of things that can give you very big improvements for gravitational waves. Everything right now is done on the surface. If we go deep underground, the shaking of the earth is much less of a problem. We make the present ones 4 kilometers in the US, 3 kilometers in Italy. We can make them longer. 10 kilometers is what the design is in Europe. We're talking about 40 kilometers in the US. You can use different topologies. For example, a triangle can have the beam going counterclockwise and clockwise and have the checks you need for precision measurements. The biggest step, I feel, is to learn how to do it cryogenically. And the reason we don't do it now cryogenically, the Japanese are trying, is that it takes R&D to understand what the right materials are for the mirrors and for the mirror coatings and how to make it cold without shaking anything, which is an engineering problem. So we're working on the R&D for how to make a good cryogenic detector. Lastly, it doesn't have to be so broadband like the present ones where we're trying to cover the whole frequency band in one detector. If we do the optics in a more specialized way, we can pick on, for example, the frequencies of a pulsar that we know of and search for it in our atmosphere. This is the evolution that we predict will happen in sensitivity. The data that I've shown you is the very top picture. It's sensitivity on the left and frequency on the right. The 2 next bands are what we've already built and just haven't made work, is the one called A-LIGO right here. LIGO A+, we're now funded for, which will bring it down to the level down here. This is a log scale on the left. So the increase of sensitivity as it increases linearly, how far out you can look, and the cube of that in terms of what you're able to see, because the volume of the universe is bigger. If you go to the next generation detectors I just showed quickly at the end, you come down to the lower lines. So you can see that even in the vision of the next tens of years, we should be able to improve the sensitivity even a factor of 100 and broaden the frequency band. That'll enable us to go in the right-hand plot, which is for the kinds of events we're looking at now, out to the edge of the universe for the black holes, for example, or at a very large Z, redshifts, so we can start to do cosmology with gravitational waves. And with that, I ran over a couple of minutes, I'm sorry. That gives you a picture, a rather broad picture of where we are and hopefully where we're going. Thank you.
Thank you very much, Professor Barish. Actually, I would like to take the opportunity to thank all the 3 speakers, opening speakers, Professor RUBBIA, Professor GLASHOW, and Professor Barish for opening our session today and giving us the honor to be present. I think we all need a little break. I would like to close now this session, and let's open just in 5 minutes to be faithful with the schedule, but please don't go away, don't leave, because our program will continue with 3 excellent highlights that you're looking forward to listen next. So thank you very much again, and meet you in 5 minutes. Thank you. Ready to start? I'm back on YouTube. Okay, we are ready to start back, and the next convener for this session is Luca Stanco, who will introduce you to the next speakers.
Thank you, Lisa. So welcome back. Good afternoon, or good evening, or good morning. So we are going to have a very high qualified session also as the second one. And the first speaker is Professor HALZEN, who will speak about astronomy with high energy neutrinos or astronomical phenomena. It depends how Francis wants to address this issue. So please, Francis.
Good morning, afternoon. I welcome the opportunity to speak at this workshop. I went to the first of these workshops at the Academia in Venice 20 years ago, probably a bit more. And we would sit around the table, guided by the wisdom of Mila-Baldo Ceolin, who told us we had to collaborate rather than compete because this was going to be very difficult. And she was right. So I will talk about what you expect me to talk about, IceCube, the status of cosmic neutrinos, and then how we are trying to figure out what type of accelerators they come from. You see here on my first slide, to remind you, the raison d'etre of neutrino astronomy is to continue the success of the astronomers of observing the universe from radio waves to gamma rays. But that success eventually runs in trouble because when you reach this demarcation line here in black, the universe becomes opaque to photons, except for those coming from our own galaxy. You can here, you see, we barely see the galactic center, but most of the universe we have never seen at these small wavelengths or high photon energies. And the reason is simple. Photons arriving from a faraway galaxy never make it to your detector if they have energies of the order of 100 TeV and more, because they interact with a microwave photon and make it plus or minus pair. And with charged particles, you cannot do astronomy. We know that because we see protons reaching us from the extragalactic universe, but the sky is scrambled by magnetic fields. And so we have no indication of their sources. Neutrinos don't have this problem. And so that was the idea went back to the 60s. That's how you investigate this dark side of the universe. Is this an interesting region? Well, of course, yes, because although we cannot do astronomy with them, we see the protons and some heavier nuclei. This is the extreme universe of particle accelerators. And just to set a scale for some of the audience not familiar with the topic, for instance, in 91, or there were some hints before, a modest experiment in Utah, the fly's eye, by today's standards modest, detected this particle that had an energy of 300 million TeV. If you build an LHC to accelerate this particle, you had to fill the orbit of Mercury with LHC magnets. How does nature do this? There are very few ideas how you can accelerate particles to this energy. Here is a classic one. You see here on the left, this is a galaxy. It's like ours, it has a supermassive black hole in it. The difference is it's an active galaxy. The supermassive black hole is eating its own galaxy. And so the matter, stars and light are swirling in. The space-time of the black hole grabs the particles falling in and winds them, the magnetic fields up and accelerates them along a jet, an axis, which is perpendicular to the spin axis of the black hole. Here is another picture of that. When the accretion into the black hole reaches the black hole, the magnetic field lines are wound up and you get a jet of particles. This is not like CERN. What you throw into the universe is a beam that's made of blobs of plasma. So that's how you have to imagine this accelerator. We actually see this happen. And whether the details of this are right or not, we really don't know at the moment. Where do neutrinos come in? Well, if this source is a cosmic ray accelerator, it will accelerate protons. But the protons are accelerated close to the black hole, but this galaxy is surrounded by electromagnetic fields and dust, and so the proton has a target to produce pions that decay into muons and neutrinos. So it's just like at Fermilab, you have a proton beam, you have a target, which is the nearby radiation or maybe molecular clouds, and then you have a beam dome that produces pions, charged pions that decay in neutrinos. And for each charged pion, 1950s physics, there is a pi zero that decays into gamma rays. And these gamma rays have actually roughly twice the energy of the neutrinos. And we know exactly how many there are. So this introduces the concept of multi-messenger astronomy. So the complete picture is that you produce pi zeros that produce electromagnetic showers along with charged pions that produce neutrinos. The problem is, how big a detector do you need to build? And years of work, the idea evolved that you actually, to have a chance to doing a neutrino astronomy, you had to build it 10,000 times the size of this detector. How to do this is an old idea as well, goes back to the 50s. Markov and his students, you look through the Earth for neutrinos coming through the Earth. They will fly through a detector you built, which is a Cherenkov detector, deep in the transparent ocean or lake water. And so you just instrument a large volume with photomultiplier tubes. And if a neutrino occasionally, like 1 in a million times in practice, interacts near or inside the detector, it will make a muon. And the muon Cherenkov cone will tell you the direction of the neutrino, so you have a telescope. All this works by standard model physics, deep inelastic scattering. This was tried back in the 80s. These people, Dumont experiment, developed these techniques. We owe a lot to them, but they unfortunately failed. And now their effort is being revived in Lake Baikal and in the Mediterranean with the ambition to build experiments of the size of IceCube. IceCube had a slightly different idea that started actually at the first Neutrino Telescope meeting. And that was to implant the photomultipliers, not in water, but in ice. And where do you find ice? You go to the geographic South Pole, where the National Science Foundation happened to have a station. Our R&D program showed that below 1.35 kilometers, there are no bubbles in the ice. And so you have a decent way to, you have a decent Cherenkov medium, which we are still trying to study and improve our understanding of. So we built IceCube, by the way, on the right here. That's the IceCube construction site at the other side of the runway of where the planes land. And so IceCube is just a collection of more than 5,000 10-inch photomultipliers in a cube of ice, an hexagonal cube, 1.4 kilometers under the geographic South Pole. You here see a muon track reconstructed, and so you see the photomultipliers along the track light up. There is an air shower array at the surface, and so this is the geometry. The details really don't matter at this point. So you build such a detector, and what does it see? It sees 100 billion muons per year, 3,000 per year, 3,000 every second. It sees more than 100,000 atmospheric neutrinos per year, 1 every 5 minutes. And that's not what we want to see. We want to see cosmic neutrinos. And in fact, to make a long story short, we see them now. And we see them at a rate of about 120, in fact, likely more per year. But so you have to find these neutrinos. It's an enormous background. And that's not that difficult because of course, as I said, you see mostly the atmospheric background. You see here the ice cube and earlier Amanda measurements of the atmospheric background, nu mu and nu e. This is slightly outdated, I'm sorry, but I want to show it because theorists told us that if you reach this level of the flux, which in this picture is multiplied by energy, so you're looking at the energy in the beam, not the number of particles. If you actually reach 100 TeV, then this flux, which is there all the time, but it becomes small. And so if you are well above 100 TeV, every event is a discovery, and I'll show you events like that. So this is also a blessing because you will see energy measurement is critical. And you can use it. It's well understood. You can calculate it. You can use it to calibrate your experiment. And here you see again the latest ice cube data superimposed with the measurement of the Antares experiment. So I've taken the Antares measurements, superimposed them here on ice cube. This is the Baikal experiment calibrating their present detector. And so you see all these measurements agree. So we have a calibrated experiment. Everybody has a calibrated experiment. We discovered cosmic neutrinos in 3 ways, actually. One way is muons coming through the Earth, which you see on the right here. It gives us tracks with very good angular resolution to do astronomy. And on the left, you can see the super K technique of looking for neutrinos starting in the detector. And that gives you total calorimetry and you get excellent energy measurement. You realize energy measurement is critical. So 2 events shown in an unconventional way. This is 1000 TeV neutrino, an electron or a tau neutrino, we don't know, superimposed on the data center in Madison, Wisconsin. You see the size of it, more than 300 PMTs report 100,000 photoelectrons, and we know where each of them is to 2 nanoseconds. This is a spectacular neutrino coming through the Earth at 11 degrees. It deposits actually 2,600 TeV inside the detector. And standard model physics predict that implies that an original neutrino energy is in the order of more than 5,000 TeV. So recently we actually saw an event which deposits 5.3 PeV inside the detector. And so that by itself is a 5 sigma discovery of cosmic neutrinos. The flux we measure, and I always show the energy flux, is from a third analysis, these black points. It just looks for showers made by electron and tau neutrinos in the ice, electromagnetic showers. And it shows this rough power law from e to the minus 2.5, which is a bit steeper than the measurement we make with the muons coming through the Earth. This flux is determined from looking at the deviation of the atmospheric flux once you reach 100 TeV, the cosmic flux. If we reconstruct the cosmic flux, we get this pink butterfly, and the 2 measurements are consistent with each flavor being produced equally, which is of course what you expect. When you look at accelerators from outside the galaxy and you collect the neutrinos after they propagated a long way, they're going to have roughly equal flavors. And that is what we measure with a big error bar. But we have an effort going on to reduce this error bar and to do oscillation physics at 1000 TeV energy. I cannot resist to this audience to show 2 events that further confirm our suspicions we are seeing extragalactic cosmic neutrinos. You know, Learned and Pagvasa discovered the idea of looking for tau interactions by looking for the interaction of the new tau in the detector, and after the tau lifetime, seeing it decay in a separate event like 50 meters later. So 1 millimeter in the donut experiment at Fermilab is for us like 50 meters. We looked for these events with 3 different analyses. They found candidates, and they all discovered this candidate, which is as a tau lifetime of 17 meters. With the precise waveforms of the light deposit in the photomultiplier tubes, this is easy to see. For instance, this is a signal, in one of the PMTs, and you see the light deposited when the tau is produced, and then you see the light deposited when the tau decays. Of course, taus of this energy are not cannot be produced in the atmosphere by oscillations. There are no oscillations at this energy, so it must be cosmic. As Professor GLASHOW already mentioned, this was a real discovery for us. It will soon be published in Nature. Neutrinos, antineutrinos, can actually produce, interact with atomic electrons. When they interact and produce real W of ATGF. He was the one who suggested this mechanism in 1960. And we found such an event. And so what it is, it happened just outside the detector, and it's a real W decaying into quark, anti-quark. So we're for the first time looking at a clear hadronic shower, and we had indeed see the muons first coming at the speed of light from the charged pion decays, and then we later, at the speed of light in the medium, in the ice, see the Cherenkov picture of the electromagnetic shower. If you actually assume this is a resonance event, you get a right cross-section for the GLASHOW resonance, and you reconstruct it, and you see our standard software reconstructed the energy right on the money. So even for a theorist, the excitement here is the calibration, not necessarily the physics. We spent a couple of years trying to figure out, when we had hundreds of high energy neutrinos, to figure out where they come from. And being unsuccessful, we published our 10 years data and carefully analyzed the sky map. You are not looking at the neutrino map of the universe. You are looking at the probability that is a neutrino source in a particular location in the sky. So this is a probability map. And the highest probability reaching the 5 sigma level is this dot, which coincides with the nearby active galaxy NGC 1068 or M77. We also discovered that this map is not symmetric, it's not isotropic. For the first time, it has an isotropy, which is due to 4 at a 3 sigma level, which is due to 4 sources. One, of course, M77, one, an active galaxy TXS 0506, which you will hear about later, and then 2 other active galaxies. Whether these are real or fluctuations, you know, they post-trial, only the asymmetry in the map reaches 3 sigma level. So we will need a better detector to figure this out, and we are not waiting for Gen 2. Once we were aware of this, we started a campaign to improve the detector for the first time. We improved the detector calibration. I cannot go into detail. The details will be published soon. Which we refer to as Pass 2. We improved the neural nets to do energy and pointing reconstruction. For the first time, we understand the point spread function of IceCube, and it's consistent with our simulations. So all unknown systematics disappeared, and we are still improving the modeling of the ice. So the conclusion is that we observe a flux of neutrinos from a uniform isotropic extragalactic universe. And what's not obvious at this point, the neutrino density of the energy density of neutrinos in this dark universe is actually roughly the same in gamma rays. And let me concentrate on this topic for a moment, because I think this is the main discovery of IceCube. Remember that there is a pi0 decay into 2 gamma rays for every charged pion decaying into neutrinos. And of course, the problem is that these gamma rays lose their energy in the universe, and maybe even in the source, and they don't reach our telescopes. However, after this E+ E- pair is formed, a cascade develops, these electrons radiate, the photons will pair produce, and so a PeV gamma ray will end up at Earth in the form of many GV gamma rays, which can be detected by the Fermi telescope, which is a pair spectrometer flying on a satellite. And so we can directly predict, this is a historic slide, this is a fit e to the minus 2.15 to our early data. You convert this to gamma rays, dump them in the microwave background, and the photon flux that comes out is consistent with the one measured by Fermi. You can massacre this correlation if you make different fits to the data, but qualitatively you cannot escape this prediction. In fact, the best fit to our many analyses that I didn't describe is actually e to the minus 2.5. Not e to the minus 2.15. And if you repeat the energy, you could see we missed this point, for instance. If you repeat the fit, you get an energy deposition in the Fermi satellite. It's much larger than what they see. So this is no problem. This means that the neutrinos most likely already lost energy in the sources before reaching the microwave background. And so they are sitting at energies below the Fermi threshold. And so this is what we refer to as dark sources. And dark sources, we have to think about, because, let me say an obvious thing, which has not been appreciated. To produce neutrinos, you don't need an accelerator. You also need a target. You need a beam dump. And so I will discuss the next topic from this point of view. Frustrated by not being able to read our neutrino sky map even after 2-3 years of data, we started sending telegrams to astronomers that told us where an interesting high energy neutrino came from, less than 1 minute after the photons hit the PMT in the ice. And so this paid off in September 17, when we found a neutrino of 290 TeV energy, which classic through the Earth neutrino. And within 0.06 degrees, there is a flaring galaxy, TXS 0506, flaring in gamma rays in the Fermi telescope. This was evidence, not a discovery. What made this really interesting, it's evidence in the sense, the sky is big, there are many things happening, so the chances this is an accident is at a level of 3 sigma. What makes this interesting is what happened afterwards, actually. It also turned out that this was a rare TeV blazar. It was discovered by magic, being flaring in, I say TeV gamma rays because the source is at a redshift of 0.3. So these were already seriously reprocessed gamma rays. So we never knew whether people paid attention to our alerts, but it turned out that after IceCube sent the alert, within just 73 seconds, an optical robotic network was looking at this source. It had been looking at this source since 2005. I'll come back to it. Swift saw it, then Fermi, MAGIC, and all these optical telescopes were trying to locate the host galaxy, which they eventually did, and realized that actually it's not nearby. It's a far away, unusual, unusual. There are nearby galaxies that astronomers think are identical, which should have 100 times the flux, and we don't see. So this was published, this multi-wavelength campaign in Science. But then, of course, we could go and look at the IceCube and Fermi archival data. We could further correlate MAGIC, HALZEN, Veritas, Cherenkov data. Then the optical observation was published. And finally, there was radio interferometry imaging of this galaxy. And I quickly go over these results. The IceCube data discovered that in 2014, there was a flare lasting about 100 days, which emitted neutrinos at the level of the Eddington limit, 10 to the 47 hours per second, a spectrum of e to the minus 2.2, and provided evidence at the 3.5 sigma level, totally independent and over and above anything I told you up to now. There, however, was no gamma ray flare, which I claim you kind of expect if you have a beam dump and a good target to produce neutrinos. Photons don't get through it. In fact, the source seemed to be daily variations, and it's only after 5 to 10 days that MAGIC started to see the TV gamma rays. So it looks like it was not a photon-emitting blazar at the time the neutrino was produced. This was confirmed by these optical telescopes that found the blazar in an off state when the neutrino was emitted. And after 2 hours, suddenly the source switched on 2 hours after the emission, the production of the neutrino. And this was only published recently because they spent a long time making sure this thing couldn't happen by accident. I will not go through their data, you have the reference, but you see here their long calibration run. And this is the biggest jump ever in this source, in the optical, which they had been looking at since late 2005. So all the indications are that this was a beam dump, not a gamma ray emitting blazar. Then the first pictures came from radio interferometry, and beyond 5 milliarc seconds, they saw that the jet emerging from the black hole suddenly lost its collimation. So something happened, possibly a target entered the beam to produce neutrinos. Remember, these are flares, so it's a short-lived beam dump. How does this happen? One of the interferometry papers claims it's a merging galaxy, and the flare happens when two jets cross occasionally. The other paper claims that the image, it's their image, is that supermassive supermassive stars move through the jet occasionally. Supermassive black stars in the host galaxy, we really don't know at the moment. But remember, there is no point applying blazar models to this source. It wasn't a blazar by all indications when the source emitted neutrinos. You see here the modeling of these bursts, so we have to figure out, we have to get more events. Yes, I'm about to finish. These are the conclusions, which I don't repeat. But, you know, the conclusion is, remember, we also measure diffuse flux. So if only a few % of the Fermi sources in the sky are beam dumps like TXS, it allows us to reproduce our diffuse flux. So that's a possible conclusion of the cosmic ray problem. I will not go through this slide. I have no plans. I just want to show you one possible interesting event. In July last year, we had another coincidence with a blazar. It happened again on top of a radio flare, so that's what made it interesting. And we here actually see in the Fermi data that when the neutrino is emitted, the radio peaks and the gamma rays disappear, as you expect from a beam dump. So this is the type of events we have to chase now. I'm sorry, most of the time we probably spent was working with LIGO and their friends to find coincidence with cosmic gravitational wave signals. We are in this business long before they even discovered binary black holes, and we will continue this until we are successful. This is the next attraction. The other next attraction is, if there is any conclusion from this talk, is that we need more neutrinos and better and more telescopes. And that's what's about to happen. We are improving our present experiment, just like LIGO, similar story, but we are working at building an experiment that's 10 times bigger. So is a detector in the Mediterranean of the coast of Catania, which is called KM3NET. And they have a plan to eventually build a detector which is 6 times the effective area of IceCube. And we are very much looking forward to a future with many telescopes and better telescopes of 10 times larger effective volume. Thank you very much. I want to thank the IceCube collaboration, which I still prefer to see this way. And on this, I conclude my talk. Sorry for going a bit over time.
Thank you, no. Thank you very much, Professor HALZEN. Always wonderful talk, I would say. I would just to advertise, but probably not everybody in the audience is aware that there is an icon on the bottom right of your Zoom screen where you can place questions and get answer. So okay. We have a question from Karina Udrea. Do you have any result about the depth intensity relation of atmospheric muon flux?
Oh, yes, we do. You know, this is part of the history. This is the first thing you measure. And so we have a wealth, of course. IceCube does a lot more, as discussed by Professor GLASHOW. We are in the business of doing neutrino oscillations at 10 GeV to 100 GeV energy, which I didn't even talk about. And so we have, you know, we see 100 billion muons per year. So if you tell me exactly what you want, so we not only have data on depth intensity relations, but also on the time evolution of the atmospheric neutrino fluxes. So if you send me an email what you want, I can provide it.
Okay, thank you very much. There is also a couple of two interesting questions, and I have to pick only one of them and let the other one on the Slack channels. So Sergei Trotsky is thanking for your interesting talk, and about the correlation TXSO 506. He is looking at the IceCube preprint, a very recent one, where you describe a new improved data set. The preprint states that the correlation is much less significant than it was originally published. Also, in the new data set, the energy of the event 170922 is 52 TeV, not 290 TeV. Can you comment on that?
Yeah, our result on this has not changed. There are two answers to this question. The 3.5 sigma observation stands. There's no change to that. That's in the 10-year physical review paper. This data set we released, you know, you can read I gave the reference. You can read, by the way, I'll use this to advertise. We released all our data and the simulation, so you can do your own astronomy. The last answer to this question is we are developing a much bigger detector, and it will answer this question, and you will see the results soon. You see these 4 sources that I advertised. At this point, you really are not sure whether these are fluctuations or they are really sources. And so we did the normal thing. We improved our analysis. We finally, after 10 years, improved our analysis, understood our telescope much better, got rid of any unknown systematics, and you will see the results soon.
Okay, thank you very much. So all the questions will be placed on the Slack channel.
Yes, I will answer.
Sorry.
I will answer them.
Okay, so thank you very much again, Francis. And now we go to Mark Kamionkowski, who will provide us with a landscape on present cosmology. Thank you very much, Mark. And please go ahead.
Can you see my slides?
Yes.
Good.
Very good.
Okay, so today I'm pleased to be here to tell you about a state of cosmology, and cosmology is a very, very broad field with lots of things going on, and so I chose to focus on one particular aspect that has received a lot of attention recently and that my collaborators and I have been thinking about as well. So I'll talk to you about cosmic tensions, and there's a question mark because this is forefront research, and this error bars are significant, the statistics are significant, but the implications are very, very serious, and so we should tread carefully when we discuss these things. So I'll tell you about some possible problems with the cosmological model and some new physics that we have been thinking about that might be implied if these tensions are not resolved through measurements. So I first wanted to mention some of the collaborators on the work. There's Tanvi Karwal, who was a graduate student at Johns Hopkins when this work began. She's now a postdoc at the University of Pennsylvania. Vivian Poulin was a postdoc at Johns Hopkins when we did this work. He is now in a CNRS position at Montpellier. Tristan Smith is an assistant professor at Swarthmore College who was on sabbatical at Johns Hopkins when we did this. Kimberly Buddy was a postdoc at Johns Hopkins. She's now moved to a faculty position at UT Austin. Jose Luis Bernal is a current postdoc involved in this work, and Simeon Bird was a postdoc for and worked on some of these things, is now faculty at UC Riverside. So the most basic characteristic of the universe, or one of the most basic features of the universe, is that it is expanding. So if we look at any given galaxy, we see that that galaxy is moving away from us with a velocity that is proportional to its distance, and the constant of proportionality, h, sometimes also written as h sub 0 to denote the value today, is the Hubble constant. So to make a long story short, or for those of you whose attention might wander, this is the current state of the measurements. And I've placed only a select few measurements on here. There are some other measurements that sort of scatter in here. But there are inferences for the value of the Hubble parameter that come from the cosmic microwave background from both Planck, WMAP originally, and then Planck, consistent value with the smaller error bar. And there are also better measurements and complementary information from ground-based experiments like ACT and SPT3G that agree. So there are values from cosmic microwave background, 67.4, and then there are values from measurements of supernovae, which are about 74. So that's about a 10% discrepancy, and the error bars are significant, and the tension is now at the more than 5 sigma level. So we use the word Hubble tension because when we first started to notice this discrepancy, it was at the 2 sigma level, and the 2 sigma level is not a discrepancy, that is a tension. But strictly speaking, this is now a full-fledged discrepancy, and although we call it the Hubble tension, for traditional purposes, it really should be thought of as a discrepancy. So the question is, why is it that these values inferred from the cosmic microwave background are so different from those obtained from direct measurements with supernovae? So the Hubble constant, so first I'm going to tell you a little bit about how these measurements are done, a little bit about how these measurements are done, and then what new physics these measurements might imply if the discrepancy survives further scrutiny. So the Hubble constant is inferred from supernovae in a fairly straightforward way. More or less the same measurement that Hubble did, close to 100 years ago. So we use type 1a supernovae, and I shouldn't say we, the observers used type 1a supernovae, and these are explosions that occur at the end of a massive star's life. And in particular, there are explosions that occur when a white dwarf has accreted just enough matter to push it over the Chandrasekhar limit, 1.4 solar masses. And for that reason, we believe that all of these supernovae have the same luminosity, and that assumption has been calibrated very well with nearby supernovae. And so we can infer the distance from the brightness of the supernova, and the velocity is very straightforward to infer. It is obtained from the redshift, the comparison of the observed frequencies of atomic spectral lines from the galaxy with the laboratory frame frequencies of those atomic transitions. And to make a long story short again, here are the results. This is the luminosity or brightness. This is the brightness of the supernova as a function of its recessional velocity, plotted in strange units. And the slope gives us the Hubble parameter. And when you do that, you get the value shown here, 74 kilometers per second per megaparsec. Now, the value of the Hubble constant that we infer from the cosmic microwave background is the inference of the Hubble constant from the cosmic microwave background is a little more complicated, but still straightforward. And I'm going to try to explain to you, roughly speaking, how that works. So when we look at the cosmic microwave background, we are looking at a spherical surface. We're seeing cosmic microwave background radiation left over from the time when electrons and protons first combined to form hydrogen atoms. And that occurred when the temperature of the universe was a few electron volts, which was approximately 14 billion years ago. And when we look at that cosmic microwave background, the photons we're seeing were released when the universe was about 400,000 years old or 380,000 years old. And these little squiggly lines are my attempt to draw galaxies. So the cosmic microwave background allows us to probe distances much farther than even the most distant galaxies. The late universe is transparent to these cosmic microwave background photons, so they travel in straight lines to us. The early universe was opaque. And so we see a snapshot of the universe, of a spherical surface in the universe as it was 380,000 years after the Big Bang. And the radius of that sphere centered on us is about 14 billion light years. And when we look at that cosmic microwave background, this is what we see. So this is a molar-wide projection of the 4 pi steradians on the sky. If this was a map of the Earth, North America would be over here, Eurasia would be over here, Antarctica would be here, Africa and Australia. And the resolution of current maps is approximately 5 arc minutes or so, or even smaller. And so we have on order several million pixels on the sky. And the color contrasts here represent hot and cold spots. The red spots are places where the temperature is larger. Blue spots is where it's a little bit lower. And the temperature variations, the color contrast is set so the temperature variations are roughly 1 part in 10 to the 5th. Now, it is from this map that we are able to infer a value for the Hubble parameter. And the way that we do that is within the context of our standard cosmological model, a cosmological model in which the expansion of the universe is understood within the context of general relativity, in which the universe is filled with several components of matter, baryons, neutrinos, cold dark matter, and a cosmological constant. So the way we look at this map is in Fourier space. And in Fourier space, the map looks like this. So this is a plot of the power spectrum. So this is a plot of the Fourier transform, the Fourier amplitude squared as a function of the wave number. So strictly speaking, this flat surface, which I show as a flat two-dimensional surface, is in fact a two-dimensional sphere. So strictly speaking, instead of doing a Fourier transform, we are doing a spherical harmonic transform, which is the spherical surface analog of a Fourier transform. So instead of talking about wave numbers k, we talk about multiple moments L. And the plot goes from L equals 2, the quadrupole, to L of several thousand. So the quadrupole shows us temperature fluctuations, roughly speaking, between points in the sky separated by 90 degrees. L of 200 corresponds to separations of roughly 1 degree. And as we go further to the right, we're getting down to fractions of roughly 1/20th of a degree. And the power spectrum looks like this. It's got bumps and wiggles. This is the temperature power spectrum, the Fourier transform of this. We can also measure the cosmic microwave background linear polarization, and this is the power spectrum for the linear polarization. And as you see, the power spectrum has very clear bumps and wiggles. And there is a lot of information in these bumps and wiggles. There is the wave numbers or angular scales at which the different peaks occur. There are the angular scales or wave numbers at which the troughs occur. There are the heights of all of these different peaks, and there are the heights of the troughs. So there's a lot of quantitative information buried in this cosmic microwave background power spectrum. Now, the peaks in this cosmic microwave background power spectrum are fairly well understood. And what happens is that they are Fourier space ringing of the Green's function for propagation of acoustic waves in the primordial plasma. So in this early universe, before the cosmic microwave background photons last scattered, during the first 380,000 years of the Big Bang, the universe is filled with a plasma of electrons and protons and photons. And that plasma is very tightly coupled because the photons scatter very effectively from 3 electrons. And that primordial plasma is very close to homogeneous, but it's not perfectly homogeneous. We do see fluctuations in the density of that plasma. And those fluctuations in the primordial plasma propagate as acoustic waves. So there are acoustic waves running around, sound waves running around in the early universe. And there is a Green's function for the propagation of those acoustic waves. And if I consider an overdensity in the primordial plasma at one particular point, if I were to consider an overdensity at one particular point in the primordial plasma at the Big Bang, that overdensity would expand in the baryon photon plasma, send out a sound wave or a shock wave that expands at the speed of sound. And so it gives rise to a fairly sharp feature. And that fairly sharp feature also occurs in the Green's function for sound waves, because the Green's function is the sound wave that would arise from a particular point at a given time. So in configuration space, there is a Green's function that has a radius that is equal to the speed of sound in that primordial plasma times the time before decoupling, 380,000 years. And in Fourier space, that fairly sharp feature gives rise to ringing, or shows up as ringing. So these acoustic peaks are determined by the sound horizon at the surface of last scatter, the distance that a sound wave could have traveled from the Big Bang until decoupling at 380,000 years after the Big Bang. So the location of these peaks, whether the first peak falls at L of 200 or 250 or 150, this location tells us the angular scale subtended by the sound horizon at the surface of last scatter. So if This is the surface of last scatter, this particular circle over here. This is the distance that a sound wave could have traveled from the time of the Big Bang until decoupling. So this is the physical distance, r sub s, that a sound wave could travel. And the angle that we measure, or that we infer from this first peak, the angular scale subtended by the sound horizon, the thing that we measure very, very precisely, we measure this to 1 part in 10,000. This angle is that sound horizon divided by the distance to the surface of last scatter. And the way we infer the Hubble parameter is that this distance to the surface of last scatter is inversely proportional to the Hubble parameter. Because if the universe is expanding more rapidly, the universe reaches its present size more quickly. If the Hubble constant is smaller, if the universe is expanding more slowly, it takes a longer time to reach its present size. And so the angular diameter distance is a bit larger. So we measure theta sub s. We know from our cosmological model the sound horizon, and from that we infer a Hubble distance. So when we do that, we get this discrepancy between the two measurements. We get 67.4 from the cosmic microwave background and 74 from the supernova measurements. So this is the Hubble tension. Why does the expansion rate inferred from the CMB differ from that observed locally? So there are 4 possible explanations. One is that there's a problem with the local measurements. A second explanation is that there's a problem with CMB measurements. If you're a cynic, there's a third explanation, which is that there are problems with both measurements. I'm not an observer, I'm not an experimentalist, so I'm not really authorized to discuss in detail these measurements. But suffice it to say that this Hubble tension has received a lot of attention from everybody in the world of cosmology: observers, theorists, people who do the supernova measurements, people who do other types of distance measures in cosmology, and from many different people who do CMB analyses. And there are no obvious problems with either sets of analyses. And so it seems like a problem that we should take seriously. And if we take it seriously, we have to think, what new physics might we be missing in the standard cosmological model to account for this discrepancy? So that is what I'll talk about now. So if we think about new physics to account for this Hubble tension, we have to be careful that this very precisely measured parameter, 1 part in 10 to the 4, is preserved by the new model, that the new model agrees with this measured sound horizon. So again, in formulas, the distance to the surface of last scatter, more precisely, d sub a, is an integral over the over time, from the time of recombination until today, of time divided by the total energy density of the universe divided by the energy density today. And we scale the time by the age of the universe today. The distance that the sound horizon, that a sound wave propagates, the sound horizon, is 1 over the Hubble rate or expansion rate at recombination, which comes from our cosmological models, times again an integral over time scaled by the time at recombination divided by the energy density of the universe divided by the energy density of the universe at recombination. And now instead of a speed of light, c, we have the sound speed, the speed at which sound waves propagate in the primordial plasma. So the point of early dark energy models is to increase the matter density at early times. So we increase rho at early times so that this denominator becomes smaller, which gives rise to a larger Hubble value that we infer from the cosmic microwave background. And roughly speaking, in order of magnitude, we have to change the energy density, this denominator, by about 10% to account for the Hubble tension. There are also late time solutions where we try to decrease the matter density at late times. Those are difficult to get to work for a variety of reasons. There's another possibility, which is to try to decrease the sound speed in the early universe. People have looked at that, but I will not discuss that. So early dark energy, how is it that we might increase the matter density at early times? So I should say that the idea was first suggested, it was sort of floating around in literature, but it was sort of suggested in a paper by Tanvi Karwal, who was a graduate student at Johns Hopkins at the time. She's now a postdoc at the University of Pennsylvania. And the idea, I already said, if the early universe expands faster, then there's less time for sound waves to propagate between the Big Bang and the time of CMB decoupling. So the sound horizon is smaller, and we therefore infer a larger value from the CMB. Now, in the standard cosmological model, in general relativity, the expansion rate of the universe is determined by the total density of matter. So this is a plot of the density of the densities of the standard components of matter in the universe as a function of redshift or time. So the Big Bang is off to the right, the universe today is off to the left, and the radiation is the blue curve. Its energy density is subdominant today, but it was dominant at redshifts greater than about 3,000. There is ordinary matter, dark matter, and baryons that was subdominant in the early universe, but was dominant over most of the later history of the universe. There's the cosmological constant, which constitutes 70% of the energy density of the universe today, but was fairly negligible at earlier times. And the total energy density of all the standard components is this red curve over here. And what we simply proposed is, suppose there's some new component of matter that we call early dark energy that behaves like a fairly large cosmological constant in the early universe, but then has an energy density that decays more rapidly than radiation in the late universe. And so its contribution to the critical density, or the total energy density as a function of time, looks something like this. It's negligible at early times, has no effect at late times, but can be roughly 10% before the time redshift of about 1100 at which cosmic microwave background photons last scatter. So this is what we postulated. We came up with two toy physics models to account for this. One of them involved a scalar field that oscillated rapidly, that was pinned at early times, and then at about the time of matter radiation equality, a redshift of 10,000 or so, began to oscillate rapidly. Another possibility is that we have a scalar field with a potential V of phi that begins displaced from the minimum of its potential, and at early times will be pinned and behave like a cosmological constant, but at late times will begin to roll and then have an energy density that decays more rapidly than radiation. So those are two toy physics models for early dark energy. And then we spent a few more years, and it's easy enough to draw these pictures, but it actually took quite a bit of effort to actually modify the calculations of the cosmic microwave background power spectra and galaxy power spectra, and then to search the parameter space for the standard cosmological models and for the parameters that describe these scalar field models to see if we could actually find a early dark energy model that allows a larger Hubble parameter while still remaining consistent with the very precise measurements of the cosmic microwave background power spectrum. And the result, which surprised me at the time because I did not think we would actually be able to get this to work, the result is that it works. And this is the money plot from the paper from fall of 2018. And this is a 4x4 cross-section of the 9-dimensional cosmological plus early dark energy parameter space. And here, for example, is the Hubble parameter versus the cold dark matter energy density. Actually, sorry. Yeah, that's yeah. So this is the Hubble parameter, a subset, a 4x4 dimensional subset of the 9x9 parameter subspace. Sorry, the 9x9 parameter likelihood space. And this little orange ellipse down here is the result in the standard lambda CDM cosmological model. So you see that the Hubble parameter inferred in the standard cosmological model from the CMB is 67 0.4 kilometers per second per megaparsec. But if we allow for early dark energy, then you see that we open up the contours and can have a value of the Hubble parameter that overlaps with the 2 sigma range from supernovae. So this shows us that we're able to get it to work. And actually, there's an important piece of information that I will tell you, although it's not shown on here. We also need to ask, are there regions of the parameter space that are consistent with a Hubble constant in this gray range over here, but that also give you a chi-squared that is consistent, a good chi-squared? And the answer is yes. So there are early dark energy models that allow a value of the Hubble parameter above 72 kilometers per second per megaparsec that have a chi-squared, a reduced chi-squared that is equivalent to that for the standard cosmological model. So the answer is that it can be made to work. The model makes predictions that will allow it to be tested against the standard cosmological model, and those predictions are for fine angular scale measurements of the cosmic microwave background polarization that will be obtained within the next 5 to 10 years, starting with ACPOL and SPT3G, but ultimately Simon's Observatory and CMB-S4. And this is a plot that indicates or shows that this is a 2-dimensional slice through the cosmological parameter space of a plot of the likelihood contours. These are, the red are the likelihood contours for Planck current measurements, and this is the fraction of the energy density that contributed by early dark energy at its peak. So this should be about 10%-ish, and this is the Hubble parameter. And the red contours indicate that current measurements are roughly equally likely to be early dark energy or Planck, but with CMB-S4 within the next, on a decade timescale or so, we do expect to be able to resolve early dark energy models from the standard cosmological models. This idea has received a lot of attention over the past 2 years, and there are a number of questions. For example, what is the new physics responsible for early dark energy? And one idea, another question is, why is it that the early dark energy transitions from cosmological constant to dynamical behavior at about the time of matter radiation equality? And for the purposes of this conference, which is focused on neutrinos, there was actually an interesting idea by Jeremy Saxton and Mark Trodden, where they suggested that that dynamical transition might be related to the transition of neutrinos from being relativistic particles in the early universe to becoming non-relativistic in the late universe. So if neutrinos have a massive order in electron volt, their transition from relativistic to non-relativistic behavior takes place coincidentally at roughly redshifts of 10,000 or so. There have been other neutrino explanations. It had early been noted that the Hubble tension could be resolved by extra relativistic degrees of freedom in the early universe, for example, sterile neutrinos, but this actually turns out to not work. It introduces new tensions with other cosmological observables. Kreisch, Racine, and Doré and others have considered the possibility that neutrino interactions might account for the Hubble tension. But I don't know whether I won't say that this idea is ruled out, but it's turned out to be difficult to get it to work in a way that's consistent with laboratory constraints to neutrino interactions. And finally, I'd like to close with a little speculation. We know that there's a cosmological constant in the universe today. We have very good reason to believe that something like inflation occurred in the early universe. And if so, that implies a very large value for a cosmological constant in the early universe. If the Hubble tension survives further scrutiny, and if it is explained by early dark energy, it suggests that there's a cosmological constant that is for temporarily non-zero until a redshift of about 10,000. And so this seems to suggest that there might be recurring periods of lambda-like behavior throughout cosmic history. And this idea was actually foreseen almost 20 years ago by several groups. So if you have a scalar field responsible for dark energy in the universe today, it can have a tracking behavior in which it has an energy density that's comparable to the ordinary matter and radiation densities throughout cosmic history. But if there's a small wiggle in that tracking oscillating energy tracking field potential, it can give rise to cosmological constant-like behavior throughout the history of the universe. This is a plot of the energy density of that scalar field as a function of scale factor of the universe today here, the Big Bang off to the left. There's also a possibility that string theory suggests. So string theory implies the existence of several hundred axion-like fields, possibly with masses distributed logarithmically. And if so, it is conceivable that each stage in the history of the universe on a logarithmic timescale, there's some chance that the axion field, if sufficiently displaced from its minimum, may act at least briefly like dark energy. So I just want to close by saying that there are actually a number of different routes being pursued now to provide independent measurements of the expansion rate to confirm or disprove the supernova measurements. There are measurements with the tip of the red giant branch. Stars at the tip of the red giant are believed to all have the same luminosity, and so those are being pursued as standard candles. Gravitational waves can be used as standard candles if we can obtain electromagnetic counterparts to figure out their host galaxies. There are ideas, actually, there are measurements now being done with with strong lensing time delays, and those are starting to provide results. So I think that in the future, we're going to have a number of different types of cosmological measurements to confirm or disprove the supernova measurements. And the CMB and large-scale structure measurements, again, are also going to receive further scrutiny and further precision with future measurements. So here's my summary. There is a tension between the Hubble parameters inferred from different measurements. One possible explanation is a period of early dark energy. This hypothesis will be tested soon with new data. I understand that the ACT-POL collaboration is actually doing the analysis, although I don't know if they'll have enough data to actually distinguish between lambda CDM and early dark energy. And there are interesting speculations that one can make if this turns out to be the explanation for the Hubble tension. Thank you.
Thank you very much, Mark. Very inspired and intriguing talk, at least to me. There are a couple of questions. One from Ali Rida Khalif. Thanks, Mark. What about a mechanism that would bring the late universe value H0 down to the CMB1? Is this... no, okay, if you may reply, otherwise... is it clear, the question?
So I'll take the first one. What about a mechanism that would bring the late universe value of H0?
Yeah.
Late value of H0 down to the CMB1. So if we're going to adopt that solution, I mean, one solution is to just discard the supernova results. If you think the supernova measurements are wrong or the interpretations are incorrect, then that solves the problem. But there turns out to be no easy such answer. Another solution would be to change the late time expansion history of the universe to decrease the energy density of the universe relative to the energy density today at redshifts between now and the surface of last scatter. And that turns out to be possible, but theoretically it is disfavored, but because it requires effectively a negative, some new constituent of matter with effectively a negative energy density. So negative energy density matter could provide a solution, but even if you're willing to allow such a ridiculous theoretical possibility, observationally there are constraints from the from galaxy surveys that also show that that sound horizon, that bump in the Green's function for the sound horizon, for the fluctuations in the primordial plasma, and so those late time solutions are difficult to get to work. So we've given a lot of thought to that possibility, but we have not been able to get it to work.
Okay, thanks. There is another question, but since I am the chairman, I take my step. You are talking about in your last slide that the early dark matter model can be tested with new data, for example. You may have.
Sorry, I think you became muted.
Sorry, I was. Excuse me. Yeah. So there is also another question. Thank you very much. I didn't. I don't know if you hear me before, but I take the opportunity to also place my question. I'm in Euclid, for example, collaboration, and that it will fly in the next year. Is that a possibility that the new data are going to be are going to test the early dark energy model? And which kind of data are you thinking of, or new data are you thinking of?
So the most direct tests for early dark energy, I think, is from the fine angular scale CMB measurements, because it's shown in this plot, although it's difficult to see because the current error bars are very large. This is the CMB polarization power spectrum, the residual and the CMB polarization power spectrum relative to the standard lambda CDM model in these different early dark energy models. And this very faint faded band over here is the projected error bars from CMB-S4. As far as Euclid and WFIRST and LSST goes, galaxy surveys, there aren't really any direct tests of early dark energy, because the modifications would be to the primordial matter power spectrum at very small scales, and those scales are those that have gone nonlinear. So it's difficult to make those tests. But on the other hand, you know, with VRO, LSST, and Euclid, we're going to have so much more power in terms of understanding and constraining many of the other you know, variables that go into the analyses, that there's going to be a lot of power there. And the other thing is, you know, if we were to discover with Euclid, for example, that W was actually different than -1 today, then it gives us far more reason to believe that, you know, dynamical dark energy exists. And, you know, the idea of having a dynamical dark energy at the time of recombination would be a little less crazy.
Okay, thank you very much. There are other questions probably that you may go to the Slack channel. So thank you very much again. And now I'm delightful to introduce to you the former INFN president, Professor Ferroni, who will talk about double beta and everything on double beta. Please, Nando.
Everything is a bit too much, okay?
Yeah, okay. I
Well,
don't.
Sorry.
You're going too fast.
No, don't worry. I have to go to the first slide. Okay, I have to talk about the prospects for neutrinoless double beta decay experiments. As Professor GLASHOW said, 10 to 26 lifetime has already been achieved, at least by 2 experiments, Kamlan-Zen and Gerda. So now I have to point to my view about the possibility of reaching 10 to 27, 10 to 28, 10 to 29. Everything started more than 8 years ago with this nice paper from Ettore Majorana. Well, the advantage is that there is no reason now to infer the existence of antineutrinos, of neutrinos, antineutrons or antineutrinos. Okay, so nice concept, but very difficult to demonstrate. Okay, so the issue is Majorana versus Dirac. Well, there is a big implication in the difference that in the Majorana case, lepton number is not conserved. Okay, the idea that neutrino are different particles from any other is because their mass, whatever it is extremely different from and smaller of the mass of any other particles we know. Okay, not a concept that brings far away by itself, but it starts the possibility of thinking two different things. Now, the only problem is that any experiment that aims to distinguish, to tell a neutrino, a Dirac neutrino from a Majorana neutrino is horribly difficult, whatever you think of it. The diagrams, depending whether you're a particle physicist, a nuclear physicist, or an atomic physicist, is this one, okay? So you want essentially to convert a nucleus into another one, making a double jump, where in one beta decay you emit a neutrino and an electron, and if Majorana theory is correct, since a neutrino and antineutrino are the same particle, at the other vertex the neutrino is reabsorbed, another electron is emitted, and you have only 2 electrons in the final state, which makes the process, at least experimentally, quite simple, because there is a definite energy. It's like a two-body decay. Okay, if you want a more elaborate diagram in terms of quarks, is this one. Okay, so lifetime. The lifetime of this process depends essentially on the phase space, on the matrix element that describe the transition, and a sort of neutrino mass, which is a combination of the 3 neutrino flavors, mass state actually. As far the phase space, this is the only easy part to calculate. It depends essentially only from the Q value of the transition. And you say that essentially most of the elements, not all the elements, not all the isotopes can undergo double beta decay, but amongst them that they can do, most of them are in the same range, okay? Selenium, molybdenum, cadmium, tellurium, xenon have essentially the same phase space. Exception is made is germanium, because germanium has a very low transition energy to MeV compared to the almost 2.53 MeV of the others. So the fact that the phase space goes with the 5th power of the Q value disfavor the germanium. As for the nuclear matrix elements, well, they're very difficult to compute. For example, we have a process which is the standard process where 2 neutrons decay at the same time in the same nucleus. This is the normal process where you emit 2 electrons and 2 neutrinos. And so you have a benchmark, at least for this process. There is a little problem. The little problem is in the axial constant, because which is known to be from neutron decay to be 1.269. However, if you take 1.269 for the double beta decay, for the normal double beta decay, and you plot it on a scale where essentially you should have almost the same value, nothing comes out right. Because in this kind of decay, is well known from the single beta decay that the axial constant goes as the one from the nucleon, from the free nucleon, multiplied by the mass number to the minus 0.18. Now, if you now you have 3 possibilities for the neutrinoless double beta decay. You're lucky and the constant is the same as the nucleon. That would be great. It is the same as in the case of the quark, which is 1, and we could live with doing the experiment. Certainly, if it goes like in the neutrino normal double beta decay, then there is a real problem for an experiment, okay? Because the sensitivity decreases by a huge factor. These are the nuclear matrix elements as computed with different methods. You could say that, of course, you know the nuclear matrix element of the 2 neutrino double beta decay, so you don't see any reason why this scatter should be. However, the nuclear matrix elements are different from the 2 processes. The 2 neutrino double beta decay is essentially a 0 Q² process. And this one, involving essentially a virtual exchange of neutrinos, is a process which is limited only by essentially the potential well of the nucleus, so can go to up to hundreds of MeV square. So this doesn't allow a direct extrapolation of one of the nuclear matrix to the other. There are other differences, we don't go into that. You see that the prediction scatters by, say, a factor 2 for the same nucleus, sometimes worse. This is then has to be squared for going into the prediction of the lifetime. So you have an intrinsic uncertainty of the factor, say, 2, 4, 6, less than 10, say. Okay. So you can make now, if you somewhat combine the phase space with a nuclear matrix element for each of the elements, and you assume, of course, a neutrino mass, standard neutrino mass of 1 electron volt, and then you assume that GA is 1. If you multiply the phase space with the square of the matrix element for a definite element, you have a reference number, okay, a lifetime, which only, of course, serves only for comparing two different nuclei. Is not the baseline for any very sound assumptions. However, you see from this plot what you expect for this neutrino mass. Of course, you can scale with the square of the neutrino mass to get the prediction for your favorite element. Okay. Now there is the third part, which enters the lifetime, the half-life, which is the neutrino mass. You have to have an effective neutrino mass because, of course, there are 3 neutrinos, so you have to combine them, and you combine them taking in account 2 Majorana phases, which are unknown. This brings to the famous plot where you have prediction for the inverted hierarchy and for the normal hierarchy, where essentially you can say that for the inverted hierarchy, the central value is in the region of 20 millielectron volt, or if you want the lower value, is in the region of 20 millielectron volt. And for the normal hierarchy, which has a funny shape that unfortunately combining properly the Majorana phase can get to a very unfavorable case of a very low effective mass. Anyhow, say the lowest value in a reasonable scenario is 2 millielectron volt. So this means that, again, going to the plot where you take one element, for example, a molybdenum 100, and for 1 electron volt for the most favorable axial constant, you would have an half-life of 410 to 23. Now, if you scale this to 20 millielectron volt, you need to go to 10 to 27. If you have 2 millielectron volt, you have to go to 10 to 29. You should be scared at this point, because although I always say to my students, don't worry, because the Avogadro number is a big number, 6, 10 to 23. When you start to go to 10 to 27 or 10 to 29, you need to put on the floor 10 to 4 or 10 to 6 moles of one isotope, which is not a very easy task. Apparently, but again, only from the calculation, because the nuclear matrix elements are not perfectly known, there is some sort of anti-correlation between the value of the phase space, which is a solid number, and the element matrix, and the value of the element matrix square. Okay, so, well, if you take this product for germanium or xenon or molybdenum, you get these 3 numbers. Well, now the measuring an half-life does not bring to the same neutrino mass prediction for different experiments. The reason is that the half-life is one of the parameters of the game. Of course, you have to have and again, the possible differences in the matrix, in the nuclear matrix element, and the different phase space. So I would say that the reach in terms of half-life of one experiment tells you the quality of the experiment, is the ability of the experiment to reach a certain value. But whether this translates into a neutrino mass, well, it will be different for two different experiments. Okay, the two parameters of the game are the number of events you expect, which is proportional to the inverse of the half-life, and the number of the background events you count. There are, here the parameter, the important parameter is the background index, which I call NB. Okay, the rest is essentially given by the better resolution you have, less background event you have. I told you this is like a two-body decay, so you have to only to measure a peak of energy. And when you take the ratio and you try to make the sensitivity of your experiment, it comes out that you end up with a square root. The sensitivity is proportional to a square root, where inside you have the mass, say the number of modes of your experiment, the time you want to run, and the inverse is given by the background index and your energy resolution. When you try to maximize the sensitivity, you don't have so many parameters to play with, okay? You cannot wait a long time, a very long time. You cannot expand the mass of your detector because it's not convenient. When you have a square root at a certain point, you don't gain much. So the energy solution is limited by the technology you have chosen. So you can only act on the background index. So I would conclude here that the square root dependency is a disgrace. Every factor 10 you want to gain in sensitivity will cost you a factor 100 in the product of those parameters, and actually the isotopic abundance and the efficiency of your experiment is a product which is limited to 1. And even worse, when you try to convert the half-life into a neutrino mass limit, then you have another square root. So the only practical way to extend the reach of your experiment is essentially to get rid of the square root. The only way to get rid of the square root is to run for enough time given by your background index, where the product essentially tell you that you can run free of background for a certain period of time for the given mass of your experiment. Of course, you have to reduce the background that you have. In this case, you get rid of the square root, and for a certain period of time, you essentially run in a zero background approximation. So this is the key. Essentially, the product of the mass times the time times the background index times the energy resolution has to be less than 1. Now, of course, as I said, let's get mass and time are not the relevant variable. The relevant number is the product of the background index times the energy resolution. This is an example. If you have 100 kilograms of an isotope and you run 1 year, suppose you have a Q value of 3 MeV. You are background free for 1 year if you have a background index of 3.3 10 to minus 4, which is the product of the, you need, sorry, background index of 10. Of course, if you want to run 1 ton for the same period of time, then you have to have an energy solution which is 10 times better. So detector options, there are 3 detector options in the double beta decay experiments. One is the brute force, to increase the mass essentially. One is the peak squeezer, you look for an extremely good energy resolution, and one is what I would call the final state judgment approach, which is seeing the track of the 2 electrons which originate from the nucleus decay. The best experiment that goes now with the peak squeezer approach is Gerda. Gerda is finished as a 0.15% full width half maximum resolution at Q value. This is the plot of the background. Essentially, the background index, which is the relevant parameter, I said, is 5.2 10 to minus 4. Okay? So essentially, if you now extrapolate the numbers, and actually the limit Gerda is obtaining is 1.8 10 to 26 here at 90% confidence level. So this means that you could run 500 kilogram of isotope for 1 year, okay? So at this background, essentially, bringing the limit close to 10 to 27. Of course, Gerda is not an experiment of 100 kilograms, as run as a mass of only 30 kilograms, but the next edition of Gerda will be Legend 200, and this will be in the right ballpark for going to 10 to 27. So the parameter that I would consider the merit factor of an experiment is the product of the background index times its energy resolution. So for Gerda, this number is 2 10 to -3, which means that you are background free essentially until 500 kilogram here. Okay, this is the plot that shows that Legend 200, which is essentially a Gerda of 200 kilograms, based on the same background index, will be able to reach 10 to 27. Of course, if you want to explore another factor 10, which means you want to go to 10 to 28, then you would have to improve the background, because even extending the 200 kilogram to 1000, which would be called the Legend 1000, would not be enough to get to 10 to 28 if you don't reduce further the background. Next option is KAMLAN-ZEN. KAMLAN-ZEN is a balloon where you dissolve xenon 136 into a scintillator. And Xenon has already run twice in 2 phases, has set a limit of 1 10 to 26. But here, although the calculation is very complex because the background index is never given explicitly, and you have to derive from the paper the numbers. If my calculation was not completely wrong, KAMLAN-ZEN was background free essentially up to 250 kilogram year, okay? But it has a mass which is already higher than that, so it's already running the square root regime. But they promise that with some improvement, essentially in the energy resolution of the scintillator, increasing the light yield, and with a balloon which is able to track essentially the alpha particle, they might reach the sensitivity of 20 millielectron volt or better to 10 to 27 year half-life in 5 years running. The third option for going to 10 to 27 is the bolometric technique, the evolution of Cuore. On the right side, you see the Cuore cryostat with the tellurium oxide crystals. This experiment will not go to 10 to 27 because it has a background index which is not up to the game. But now, if you make a double readout and you read not only the heat signal, but also the light signal, you will eliminate all the alpha particles, which constitute most of the background. You substitute tellurium with molybdenum, which has a Q value of 3 MeV, and you put everything inside the Cuore cryostat, and this is the prediction for Cupid. So the claim at this point is that the merit factor is 5 10 to -4. This would allow to do essentially to 2000 kilogram year of background free. 10 to 27 that would be reachable. However, you have to notice that here you don't have, like in case of germanium or xenon, a single nucleus. Yeah, you have a compound, which is a lithium molybdate. So while the background goes as the 2000 kilogram, the signal only goes by the molybdenum 100, proportion of molybdenum 100, which is a bit more than half of it. So 10 to 27 is reachable, not easy, but reachable. 10 to 28, well, one possibility is that I said that Legend mid-1000 with a better background might get there. One is the evolution of EXO, which is an experiment run in the United States, xenon, liquid xenon. Going to the next edition, which is NEXO, 5 tons of enriched liquid xenon. Well, it's a combination of brute force and the pick squeezer. The energy resolution is certainly not the same as the bolometers or the Gerda calorimeter or the germanium calorimeter, but still is reasonable. Moreover, you can make a clever use of the fact that you have a large volume where essentially the background index evolve going from outside to inside. So you make a proper combination of you weight the events properly. The claim is that you can get in 10 years, which is a very long time, essentially close to 10 to 28 as a limit. The sensitivity for discovery at 3 sigma is always smaller than that. There is a prospect which is very nice experiment, which has a long way to go, which is next. Next is based on gaseous xenon at high pressure, is a TPC. There are steps, demonstrator of the technology of 1 kilogram, characterization of background with a 10 kilogram, a real detector of 100 kilogram, and then a final detector, which would be called BEXT, of at least 1 ton, that could add 2 more features. So one feature would be a magnetic field. You see here, this is a TPC, so you can track the 2 electrons. So with a magnetic field, this is certainly a better characterization of the signal. And then almost science fiction, but not so, which is barium tagging with the xenon 136 decay, double beta decay decays into barium++. So if you are able to shine a laser on the barium, induce a transition, and then shine a laser of another light on the new meta state where you arrived, eventually you have a cascade of photons, red photons, which might signal the single event as belonging to a double beta process. Okay, as I said, long way to go. However, this experiment, they claim of 1 ton, background index 10 to -4, 10 to 27 achievable. With the barium tagging, then the plan would be to get to essentially a background index of 10 to 10 to -6, a very good energy solution obtained in the prototype. So in principle, you could run 80 tons here background free. Well, the only things I can say is audentes fortuna juvat. So 10 to 28, pretty difficult. Now, what's the problem with 10 to 29? So far, we have concentrated on reducing the background because the issue was in getting a couple of events with 0 background. The problem with 10 to 29 is that before talking of the background, you have talked about signal. This table, which I took from the paper, which is mentioned on the top part of the transparency, tells you how many tons of an isotope you need to get 1 event here with an half-life of 10 to 29 years. So, for example, you would need 50 tons essentially of xenon, okay? Or 24 tons of tellurium-130. Now, what is the problem? The problem is that to get 50 tons of xenon, you have to process 500 tons of xenon-136. And this looks very difficult. I strongly doubt that 500 tons of xenon even exist on Earth. I mean, so in a sense, here, if you don't want to go to the process of enrichment, which looks unfeasible, I have to remind you that most of the isotopes are in the isotopic abundance of germanium, of molybdenum 100, of selenium-82, are in the region of 5 to 8%. So the enrichment is pretty costly. And you cannot afford to process hundreds of tons to get your isotope. So here the only possibility looks to go to tellurium, because tellurium-130 is the only isotope which has an abundance of 34%. So here you might afford not to enrich, and you make an experiment with natural tellurium. So you could do an experiment with, say, 100 to 200 tons of natural tellurium. The only problem is what you do with 200 tons of natural tellurium. Where do you, how do you exploit them, okay, in an experiment? Well, there is a demonstrator, I would call, an R&D going on at SNO, where they are dissolving tellurium-130 in a form of a molecule, which is a tellurium or butadenediol complex, inside the liquid scintillator. So they are essentially trying to assess how much tellurium you can dissolve into a liquid scintillator before being limited in the light that you collect. This is something that I don't know where it goes. It's not even started in a sense. So the potentiality of this experiment, I don't know. But if it works, if you could reach a sizable percentage of tellurium dissolved into a liquid scintillator, then you could think to an experiment where, for example, you take Juno at the end of its life, after it has measured all the neutrino parameters in a great way, and they use these 20 tons of scintillator to dissolve a few hundred tons of tellurium, okay? Well, this is doable. The only problem is that you have a background. Now, there are backgrounds that, as I think BARISH was mentioning, there are things that you might do and you might want to do is technology, probably at a certain point. There are two backgrounds that are not technology, that are physics. One is the two neutrino background, which at the end depends on your energy resolution. So part of this, at the end of the spectrum, these events, some of these events will end in your region of interest. And the other is the boronate from sun. Boronate from the sun, that of course is a flat energy distribution, which of course will go under your region of interest. Now, about the two neutrinos, I have nothing to say. About the neutrinos from the sun, well, then you can tag the direction if you are very good. Of course, this means that you cannot use the scintillation light, but you have to use the Cherenkov light. This is a dream, but frankly, I do not see any other way to go to 10 to 29. This is a plot, again, taken by the same paper that say, given the fiducial volume in kilotons, how much tellurium isotope you have to dissolve, okay, to get to this 10 to 29 lifetime for a 2.5 milli-electron volt Majorana mass, assuming a certain value for the nuclear matrix element, which makes sense. And certainly that is not the limit to the experiment. Okay, so you want to start to consider to this possibility for the far future. Well, this is one. Last. Cosmology, since we had the previous talk from cosmology, now there are, as people said, hints that the neutrino mass are limited at 100, 120 electron volt, and this comes from the analysis of the cosmology data. For example, this is one the plot which show bottom right, which show essentially the neutrino mass, which is in fact probably below 120 MeV. Now, if you process this, okay, if you process this data, as these people has done in their paper, and you give essentially a central value and an error to that, limiting the possibility of this neutrino to go to 120 MeV, and taking account that there are three neutrino kinds and the difference of masses is known, then you essentially have a plane where you have the region of inaccessibility, because there is no way, whatever you do, you will never get there. There is a region which is called exploration, and one region which is called observation. Observation means that if you are able to do an experiment which reach a sensitivity of 1, 2, 5, or 10 milli-electron volt, and whatever is the neutrino mass, okay, whatever is the Majorana phase, you are in the observation region. Okay, you might be lucky that the most favorable, the Majorana phases combine in a favorable way, and then you are in the exploration. You are in the exploration region. So you can design essentially your experiment to to target one of these regions, and there is also a table of probability. If you really believe in what comes from cosmology, I think this is a very instructive plot. So my conclusion is that 10 to 27 is reachable. It will be reached probably by Legend 200 or even by KAMIONKOWSKI or by Cupid. 10 to 28 is very difficult. It's probably something for Legend 1000, for Nexo, next, okay. Let's see. Let's see. 10 to 29 is halfway between a dream and a long and tortuous way without certainty of success. That's it.
Thank you very much, Professor Ferroni. I find it very interesting, detailed, and comprehensive at the same time. And I have a question. So Legend, KAMLAND, and Cupid will probably be able to wash out completely the inverse hierarchy region, right? And this is one.
Luca, this is only in the assumption that GA is larger than 1. Okay, would say.
Yeah. So, but in any case, what is more relevant, at least to me, is that this kind of experiments should reach, I mean, the inverse hierarchy, because this would be a fixed, clear point in the theory. If double beta would be able to clearly say that the inverse hierarchy in the searches is not valid, that would be a clear point. Try to go to study the normal hierarchy region. Does it make sense, really?
Luca,
also because it will take, I don't know, for Juno, 15 years, something like this.
But Luca, the problem is that these experiments are not done for ruling out or confirming one kind of hierarchy. These are for telling whether neutrinos are Majorana or not.
Yeah, okay.
So if they are Dirac, it doesn't make any sense. I mean, ruling out inverted hierarchy exists also for Dirac neutrinos, but there is no problem, I mean, with that.
Yeah, it depends if a way is viable or not, if it is, I mean, okay, I understand. Are different things. So thank you again, Nando. There was a question from Carlo. Carlo, you may try to comment now. Carlo, if you like. I don't know. Maybe it's not. It's no more available. So I think that we end this very interesting session. We had to we heard about I think 3 examples of very tough studies and analysis. All the 3 absolutely, I'm absolutely convinced that they will deserve a Nobel Prize, and we will see in the near future what will happen. And this end of the session, I thanks again all the 3 speakers. Mauro, you want to say anything for the end of the first day?
I also thanks to the speaker. I would like only to remark, pray them to upload the slide to the website.
Okay, see you tomorrow then.
Excuse me, I have a little question here. Rubbia, I'd like to know.
Okay, please, Carlo.
I would like to know where can we find the minutes of the presentations today? The text. Is it available somewhere?
No, the slides will be available in the Indico pages.
Did you say before?
The slides will be available.
Very good. So we can go back and read what has been done.
Yes.
Thank you very much. Appreciate it.
Okay, thank you. Thank you, Carlo. Okay.
Luca, sorry, let me also add that if you visit the YouTube channels later on, you will find the recording of the whole day. So you can, in principle, listen to the whole event today by watching it on YouTube.
Okay. Bye.